So we are at a moment where I think the computational power, it's really at the level, at the maximal level, maybe a bit better, but nothing exceptional. It's not going to be like 1,000 times better. And but mathematically, as I say, there are many challenges, and I think once we will understand better how AI works, why it works, how to improve it, how to make it more efficient, safer, and everything, this is when we will see a next revolution.
I mean, if you have theory but without practical case, so you find, you kind of lose a sense of purpose. Whereas, here, if you do also the practice but without a good theory, well, you will continue on improving already known techniques, but you will not do something revolutionary. I mean, of course, you will advance the technology, but basically you will be in the same trend. I mean, you will just add some new layer of refinement, but it will not be a step forward somehow.
So we think that, of course, when you are a theoretician, you are looking for understanding. But when you are an engineer, you are looking for something which works better. But then there is a miracle that usually when you get better understanding, you become more efficient. So here what we need is, in some sense, to enrich the amount of mathematical knowledge of the computer scientists we talk with, in order to make them realize that they can try to implement larger schemes.
就比如说是像那个大型语言模型，它里面最基础的模块是 transformer。transformer 实际上基本来说90%以上都是矩阵运算。这些矩阵运算我们如何给它加速？如果说我们能够加进很多数学的东西，就比如说利用好的矩阵分解、张量分解，利用比较好的核函数的设计，以及利用比较好的那个位置编码的方式，我相信是可以更有效的去加速整个大型语言模型的计算。
I studied mathematics. I developed new methods for solar physics. And then during conferences, I met people from cardiology. They showed their time series, their measurements, and looked very similar as solar activity. And then this is a way of interdisciplinary. Then we talked with each other and worked with each other. But the important point is each discipline has its own language, specific language. And the problem is that you have to learn, each side has to learn a bit the basic parts, not complete, but basic parts of the language of the others, that we really can communicate and that they can tell what are their real problems.
比如说可以从黄大年开始，比如黄大年可以提供一系列的数学的课程，比如说是一些跟那个 AI 相关的数学，或者说跟其他方面，跟研究物理、跟材料、化学都需要不同的数学。从最简单的方程式开始，慢慢一步步的把这个问题给解剖开来，往深的方向走，就看你的兴趣。觉得要有一个好的一个提供知识的平台，我觉得需要形成一个这样的机制。 数学是最赤裸裸的东西，它直接告诉你一个事情的一个现象的本质，背后的本质是什么。
And mathematics is really something that once you understand it, you can see the beauty of it. You can see the kind of creativity. For some things it's like art. If we think about everything which surrounds us, the technology, the laws of physics that describe what happens in nature, we can use them, we can do something with them. We have the technology that we have because there is mathematics. Mathematics has been the way for the human to understand phenomena.
That in fact, by now there are in fact many parts of mathematics which have become interesting for applications. So many more than a few decades ago.
应用往往是一门综合学科。even 在数学里面，你要解决一个应用数学解决问题，不是一个单门的理论数学可以解决，这实际上是一个系统工程，数学的系统工程。
So we are at a moment where I think the computational power, it's really at the maximal level, maybe a bit better, but nothing exceptional. It's not going to be like 1,000 times better. But mathematically, as I say, there are many challenges, and I think once we will understand better how AI works, why it works, how to improve it, how to make it more efficient, safer, and everything, this is when we will see a next revolution.
I mean, if you have theory but without practical case, so you find, you kind of lose a sense of purpose. Whereas, here, if you do also the practice but without a good theory, well, you will continue on improving already known techniques, but you will not do something revolutionary. I mean, of course, you will advance the technology, but basically you will be in the same trend. I mean, we'll just add some new layer of refinement, but it will not be a step forward somehow.
So we think that, of course, when you are a theoretician, you are looking for understanding. But when you are an engineer, you are looking for something which works better. But then there is a miracle that usually when you get better understanding, you become more efficient. So here what we need is in some sense to enrich the amount of mathematical knowledge of the computer scientists we talk with in order to make them realize that they can try to implement larger schemes.
就比如说是像那个大型语言模型，它里面最基础的模块是 transformer。transformer 实际上基本来说90%以上都是矩阵运算。这些矩阵运算我们如何给它加速？如果说我们能够加进很多数学的东西，就比如说利用好的矩阵分解、张量分解，利用比较好的核函数的设计，以及利用比较好的那个位置编码的方式，我相信是可以更有效的去加速整个大型语言模型的计算。
I studied mathematics. I developed new methods for solar physics. And then during conferences, I met people from cardiology. They showed their time series, their measurements, and looked very similar as solar activity. And then this is a way of interdisciplinary. Then we talked with each other and worked with each other. But the important point is each discipline has its own language, specific language. And the problem is that you have to learn, each side has to learn a bit the basic parts, not complete, but basic parts of the language of the others, that we really can communicate and that they can tell what are their real problems.
比如说可以从黄大年开始，比如黄大年可以提供一系列的数学的课程，比如说是一些跟那个 AI 相关的数学，或者说跟其他方面，跟研究物理、跟材料、化学都需要不同的数学。从最简单的方程式开始，慢慢一步步的把这个问题给解剖开来，往深的方向走，就看你的兴趣。其实要有一个好的一个提供知识的平台，我觉得需要形成一个这样的机制。数学是最赤裸裸的东西，它直接告诉你一个事情的一个现象的本质，背后的本质是什么。
And mathematics is really something that once you understand it, you can see the beauty of it. You can see the kind of creativity. For some things it's like art. If we think about everything which surrounds us, the technology, the laws of physics that describe what happens in nature, we can use them, we can do something with them. We have the technology that we have because there is mathematics. Mathematics has been the way for the human to understand phenomena.
That in fact, by now there are in fact many parts of mathematics which have become interesting for applications. So many more than a few decades ago.
应用往往是一门综合学科 ，even 在数学里面，你要解决一个应用数学解决问题，你不是一个单门的理论数学可以解决，这实际上是一个系统工程，数学的系统工程。
So we are at a moment where I think the computational power, it's really at the maximal level, maybe a bit better, but nothing exceptional. It's not going to be like 1,000 times better. But mathematically, as I say, there are many challenges, and I think once we will understand better how AI works, why it works, how to improve it, how to make it more efficient, safer, and everything, this is when we will see a next revolution.
I mean, if you have theory but without practical case, so you find, you kind of lose a sense of purpose. Whereas, here, if you do also the practice but without a good theory, well, you will continue on improving already known techniques, but you will not do something revolutionary. I mean, of course, you will advance the technology, but basically you will be in the same trend. I mean, we'll just add some new layer of refinement, but it will not be a step forward somehow.
So we think that, of course, when you are a theoretician, you are looking for understanding. But when you are an engineer, you are looking for something which works better. But then there is a miracle that usually when you get better understanding, you become more efficient. So here what we need is in some sense to enrich the amount of mathematical knowledge of the computer scientists we talk with in order to make them realize that they can try to implement larger schemes.
就比如说是像那个大型语言模型，它里面最基础的模块是 transformer。transformer 实际上基本来说90%以上都是矩阵运算。这些矩阵运算我们如何给它加速？如果说我们能够加进很多数学的东西，就比如说利用好的矩阵分解、张量分解，利用比较好的核函数的设计，以及利用比较好的那个位置编码的方式，我相信是可以更有效的去加速整个大型语言模型的计算。
I studied mathematics. I developed new methods for solar physics. And then during conferences, I met people from cardiology. They showed their time series, their measurements, and looked very similar as solar activity. And then this is a way of interdisciplinary. Then we talked with each other and worked with each other. But the important point is each discipline has its own language, specific language. And the problem is that you have to learn, each side has to learn a bit the basic parts, not complete, but basic parts of the language of the others, that we really can communicate and that they can tell what are their real problems.
比如说可以从黄大年开始，你比如黄大年可以提供一系列的数学的课程，比如说是一些跟那个 AI 相关的数学，或者说跟其他方面，跟研究物理、跟材料、化学都需要不同的数学。从最简单的方程式开始，慢慢一步步的把这个问题给解剖开来，往深的方向走。就看你的兴趣，觉得要有一个好的一个提供知识的平台，我觉得需要形成一个这样的机制。数学是最赤裸裸的东西，它直接告诉你一个事情的一个现象的本质，背后的本质是什么。
And mathematics is really something that once you understand it, you can see the beauty of it. You can see the kind of creativity. For some things it's like art. If we think about everything which surrounds us, the technology, the laws of physics that describe what happens in nature, we can use them, we can do something with them. We have the technology that we have because there is mathematics. Mathematics has been the way for the human to understand phenomena.
That, in fact, by now there are, in fact, many parts of mathematics which have become interesting for applications. So many more than a few decades ago.
应用往往是一门综合学科 ，even 在数学里面，你要解决一个应用数学解决问题，你不是一个单门的理论数学可以解决，这实际上是一个系统工程，数学的系统工程。
So we are at a moment where I think the computational power, it's really at the maximal level, maybe a bit better, but nothing exceptional. It's not going to be like 1,000 times better. And but mathematically, as I say, there are many challenges, and I think once we will understand better how AI works, why it works, how to improve it, how to make it more efficient, safer, and everything, this is when we will see a next revolution.
I mean, if you have theory but without practical case, so you find, you kind of lose a sense of purpose. Whereas, here, if you do also the practice but without a good theory, well, you will continue on improving already known techniques, but you will not do something revolutionary. I mean, of course, you will advance the technology, but basically you will be in the same trend. I mean, we'll just add some new layer of refinement, but it will not be a step forward somehow.
So we think that, of course, when you are a theoretician, you are looking for understanding. But when you are an engineer, you are looking for something which works better. But then there is a miracle that usually when you get better understanding, you become more efficient. So here what we need is in some sense to enrich the amount of mathematical knowledge of the computer scientists we talk with in order to make them realize that they can try to implement larger schemes.
就比如说是像那个大型语言模型，它里面最基础的模块是 transformer。transformer 实际上基本来说90%以上都是矩阵运算。这些矩阵运算我们如何给它加速？如果说我们能够加进很多数学的东西，就比如说利用好的矩阵分解、张量分解，利用比较好的核函数的设计，以及利用比较好的那个位置编码的方式，我相信是可以更有效的去加速整个大型语言模型的计算。
I studied mathematics. I developed new methods for solar physics. And then during conferences, I met people from cardiology. They showed their time series, their measurements, and looked very similar as solar activity. And then this is a way of interdisciplinary. Then we talked with each other and worked with each other. But the important point is each discipline has its own language, specific language. And the problem is that you have to learn, each side has to learn a bit the basic parts, not complete, but basic parts of the language of the others, that we really can communicate and that they can tell what are their real problems.
比如说可以从黄大年开始，比如黄大年可以提供一系列的数学的课程，比如说是一些跟那个 AI 相关的数学，或者说跟其他方面，跟研究物理、跟材料化学都需要不同的数学。从最简单的方程式开始，慢慢一步步的把这个问题给解剖开来，往深的方向走。就看你的兴趣，觉得要有一个好的一个提供知识的平台，我觉得需要形成一个这样的机制。 数学是最赤裸裸的东西，它直接告诉你一个事情的一个现象的本质，背后的本质是什么。
And mathematics is really something that once you understand it, you can see the beauty of it. You can see the kind of creativity. For some things it's like art. If we think about everything which surrounds us, the technology, the laws of physics that describe what happens in nature, we can use them, we can do something with them. We have the technology that we have because there is mathematics. Mathematics has been the way for the human to understand phenomena.
That in fact, by now there are in fact many parts of mathematics which have become interesting for applications. So many more than a few decades ago.
应用往往是一门综合学科 ，even 在数学里面，你要解决一个应用数学解决问题，不是一个单门的理论数学可以解决，这实际上是一个系统工程，数学的系统工程。
So we are at a moment where I think the computational power, it's really at the maximal level, maybe a bit better, but nothing exceptional. It's not going to be like 1,000 times better. But mathematically, as I say, there are many challenges, and I think once we will understand better how AI works, why it works, how to improve it, how to make it more efficient, safer, and everything, this is when we will see a next revolution.
I mean, if you have theory but without practical case, so you find, you kind of lose a sense of purpose. Whereas, here, if you do also the practice but without a good theory, well, you will continue on improving already known techniques, but you will not do something revolutionary. I mean, of course, you will advance the technology, but basically you will be in the same trend. I mean, we'll just add some new layer of refinement, but it will not be a step forward somehow.
So we think that, of course, when you are a theoretician, you are looking for understanding. But when you are an engineer, you are looking for something which works better. But then there is a miracle that usually when you get better understanding, you become more efficient. So here what we need is, in some sense, to enrich the amount of mathematical knowledge of the computer scientists we talk with, in order to make them realize that they can try to implement larger schemes.
就比如说是像那个大型语言模型，它里面最基础的模块是 transformer。transformer 实际上基本来说90%以上都是矩阵运算。这些矩阵运算我们如何给它加速？如果说我们能够加进很多数学的东西，就比如说利用好的矩阵分解、张量分解，利用比较好的核函数的设计，以及利用比较好的那个位置编码的方式，我相信是可以更有效的去加速整个大型语言模型的计算。
I studied mathematics. I developed new methods for solar physics. And then during conferences, I met people from cardiology. They showed their time series, their measurements, and looked very similar as solar activity. And then this is a way of interdisciplinary. Then we talked with each other and worked with each other, but the important point is each discipline has its own language, specific language. And the problem is that you have to learn, each side has to learn a bit the basic parts, not complete, but basic parts of the language of the others, that we really can communicate and that they can tell what are their real problems.
比如说可以从黄大年开始，比如黄大年可以提供一系列的数学的课程，比如说是一些跟那个 AI 相关的数学，或者说跟其他方面，跟研究物理、跟材料、化学都需要不同的数学。从最简单的方程式开始，慢慢一步步的把这个问题给解剖开来，往深的方向走，就看你的兴趣。觉得要有一个好的一个提供知识的平台，我觉得需要形成一个这样的机制。数学是最赤裸裸的东西，它直接告诉你一个事情的一个现象的本质，背后的本质是什么。
And mathematics is really something that once you understand it, you can see the beauty of it. You can see the kind of creativity. For some things it's like art. If we think about everything which surrounds us, the technology, the laws of physics that describe what happens in nature, we can use them, we can do something with them. We have the technology that we have because there is mathematics. Mathematics has been the way for the human to understand phenomena.
That in fact, by now there are in fact many parts of mathematics which have become interesting for applications. So many more than a few decades ago.
应用往往是一门综合学科。even 在数学里面，你要解决一个应用数学解决问题，不是一个单门的理论数学可以解决，这实际上是一个系统工程，数学的系统工程。
So we are at a moment where I think the computational power, it's really at the maximal level, maybe a bit better, but nothing exceptional. It's not going to be like 1,000 times better. And but mathematically, as I say, there are many challenges, and I think once we will understand better how AI works, why it works, how to improve it, how to make it more efficient, safer, and everything, this is when we will see a next revolution.
I mean, if you have theory but without practical case, so you find, you kind of lose a sense of purpose. Whereas, here, if you do also the practice but without a good theory, Well, you will continue on improving already known techniques, but you will not do something revolutionary. I mean, of course, you will advance the technology, but basically you will be in the same trend. I mean, you will just add some new layer of refinement, but it will not be a step forward somehow.
So we think that, of course, when you are a theoretician, you are looking for understanding. But when you are an engineer, you are looking for something which works better. But then there is a miracle that usually when you get better understanding, you become more efficient. So here what we need is, in some sense, to enrich the amount of mathematical knowledge of the computer scientists we talk with, in order to make them realize that they can try to implement larger schemes.
就比如说是像那个大型语言模型，它里面最基础的模块是 transformer。transformer 实际上基本来说90%以上都是矩阵运算。这些矩阵运算我们如何给它加速？如果说我们能够加进很多数学的东西，就比如说利用好的矩阵分解、张量分解，利用比较好的核函数的设计，以及利用比较好的那个位置编码的方式，我相信是可以更有效的去。
Professor, take the floor.
Thank you, Piotr, for the introduction, and hello, everyone. It is really a pleasure and an honor to speak in this very nice workshop. So, so here's my topic. Well, we are mathematicians, and we like problem solving, right? Many researchers like to solve problems in their respective areas, but mathematicians are somewhat particular, right? We have our own problems. So besides solving problems, mathematicians also like to build theories, but every now and then you stuck upon a stubborn problem and you have to come up with some new ideas, with some new tricks, with some new techniques, new methods, right? So it's actually a very good idea to have a relatively large repertoire of techniques that you can try every now and then, right? So try every single one, maybe one of them will work. Well, pretty much the whole talk today will be about the one single cute idea that can sometimes help. It cannot help all the time for every single problem, but even if it helps for, I don't know, like 10% of problems, and even if it helps a little bit, that's already something, right? So first, a bit generally, when we talk about solving problems, there are two mathematical names that could probably stand out because they're usually related to problem solving. Like both of them are Hungary-born mathematicians that became quite international in their careers, in their lives. George Polya wrote many very nice books, very many methodological treatises on solving problems, and he's probably the most quotable mathematician regarding those things, right? So he would say that problem solving can happen at many levels, right? Problem solving happens at the competition level. Problem solving is present even when you want to study certain new field, right? You first want to try things on your own because that's how you understand things better. But also problem solving happens at the level of mathematical research, right? You maybe take upon a new problem that is still open, and maybe you wanna try to do something on that problem, to do something similar, and so on. So that's what he said in this regard. Paul Erdős, on the other hand, his whole life was problem solving. So pretty much he just traveled around, talked to people, talked to mathematicians. He really lived it, right? Pretty much he didn't have a home, he didn't have a permanent address. He just pretty much collaborated, solved some problems, asked new problems, solved some more problems, posed some more problems, and he just went around all his life, all his fruitful career, right? Well, okay, that's about it. But as I said, if problem solving is difficult, any trick can help. So today we'll talk about some tricks for proving inequalities or for proving estimates. So, every estimate can, in a very general and maybe even too general way, be written like you have a left-hand side, you have a right-hand side, right? But suppose that in a particular situation, you can prove something weaker. I'm not being very precise what weaker means, but maybe you cannot really prove the estimate that you want, but you can maybe lose a constant. This constant could be a million, a billion, trillion, or whatever, right? Doesn't really matter. Or it could be even worse, right? It could depend on many things that you see on the left-hand side or the right-hand side on which it shouldn't depend, right? So this is bad, right? Also, an equivalent way of phrasing this is maybe you have some very small constant that you can put on the left-hand side, and this can already make your life much easier, right? So this C could be like a very tiny, very small constant. And again, it could be even worse than that, right? It could depend on some X that you already see here, and that's very bad, right? But then maybe there are some tricks that can help you go back to what you want, right? So maybe in this particular situation, there is a way of going back and recovering what you wanted with somehow less effort invested, right? Because all you had to prove was something much weaker, something at least formally simpler than what you had initially. So since this is so general, it doesn't pretty much mean anything. So this is best explained in concrete examples. And I'll try to give very versatile examples. Pretty much there will be bits of everything. I'll try to touch upon pretty much every mathematical area. At least I'll try to approach it somehow with a sufficiently simple and elementary example, right? So you won't see anything very deep, but you see a bunch of nice tricks that apply to in many mathematical areas. Well, when you speak about inequalities, well, probably the simplest inequality that everybody learns when they start practicing for mathematical competitions is a very basic and elementary one. It's an inequality between an arithmetic mean and the geometric mean, right? So this is like so nice and simple. So the arithmetic mean, of course, of several numbers is computed in the usual way. This is the arithmetic mean. So pretty much it's the usual average, right? This is the way how students calculate their GPA, their grade point average. This is the usual average that is understood if you don't say anything else. On the other hand, the geometric mean is just the nth root of the product. But it also satisfies many properties that you would expect from an average, from a mean, right? It's certainly between the smallest and the largest number, if the numbers are non-negative. And of course, there is a bunch of other means, right? But those two are the most basic ones. And everyone knows, whoever practiced for mathematical competitions, that the arithmetic mean is always greater than or equal to the geometric mean, right? Here I chose to write this as this nth root as raising to the power 1 over n. But that's it. And there are many proofs of this inequality. It's not entirely trivial, but once you've seen the tricks, then you certainly remember. Of course, there is some cute tricks using convexity or some differentiation. There is a backward induction trick and so on. But here is like a very cute trick that looks like an overkill. Why do we have to do so much hassle about such simple inequality? But it is a cute trick invented by Harold Bohr, a well-known mathematician who actually even published this in a regular journal about 90 years ago. Harald Bohr was a Danish mathematician and a professional soccer player. So he even competed for the Danish national team in the World Cup in 1908, actually. Right? So he was both a mathematician and a professional soccer player, and he is also known as a brother of the famous physicist Niels Bohr. Right? That's his brother. So he came up with the following trick. So suppose that you want to approach the problem like very, very naively, to do something that you already know, you have some experience about inequalities, you kind of know that it won't work, right? So suppose that you very naively want to raise this to the nth power, right? Start expanding it out, multiplying it out, like just to see what you get, right? Okay, of course, raising the whole sum of n terms to the nth power is a bit complicated in a combinatorial sense, right? So pretty much you have n pairs of parentheses and you take a single term from each of them, right? So for some of these terms, you'll get the product that you see in the geometric mean. And this is good, but for most of them you won't, right? You'll see A1 times A1 times maybe A2 times maybe A5 and so on. Look, most of the terms are bad, but quite a few of them are good, right? So how often does it happen that, that a certain term is good, right? Well, it happens precisely when you take different terms from each pair of parentheses, right? So if from some you take A1, from another you take A2, from another take A3, and so on, you see that you can choose this sequence of terms in n factorial ways, right? It's just a matter of permuting the parentheses, permuting the order in which you take terms respectively. Okay, then you say, well, at least it's something, right? So if I take the nth root, right, I get some inequality. See, the sum is greater than or equal to n factorial, now raised to 1 over n, and here we have a geometric mean, right? Okay, and now the factorials look a bit ugly, so you want to estimate them somehow, right? You want to get rid of the factorials. Well, it's not very difficult. There is an elementary estimate. I want it to be sharp, so I put the constant e, but it's not very important. So e is a very particular constant. It's a base of natural logarithm, 2.71, 8281, 82845. It doesn't really matter. Right? It's just some particular constant, but it's between 2 and 3. That's the only important thing right now. So here is a very elementary inequality, right? You can bound factorials below by n over e raised to the nth power. Well, a bit later we'll need more precise asymptotics that I'm sure that you also know. But for now, this is already enough. And this can be proved in a very elementary way, right? By mathematical induction, suppose, right? For instance, 1 factorial is just 1, right? And on the other hand, you have 1 over e raised to the first power. Well, it's clear that it's fine, right? That's okay. Now, if you want to prove this by the mathematical induction, then by assuming that what you see on the board is valid for some particular positive integer n, you want to prove that it's still true for the successor, right? For the following one. Well, then what you do is just write this factorial as n factorial times the last term, apply the induction hypothesis, and then multiply with n plus 1, which is what else you need, right? And then you wonder if this is maybe now fine. Then you wonder if this is greater than or equal to n plus 1 over e raised to n plus first power. But then this question mark can be easily rewritten, right? Just take all those e's to one side, and you see that here we have e to the negative n, and here we have e to the n plus first power. So just e is greater than, and then you shuffle this a little bit. You see this cancels with this first power, and what you have is going to be n plus 1 over n raised to the nth power. But if you had some calculus, then you actually remember that this sequence increases, and in the limit you actually cover e, so it's fine, right? Even we don't read much of a proof. I'm not going in those details. But as I said, even this e is not that important. Anything would be okay. Then you plug it in, take the root. What do you get? Well, not quite what we wanted, right? So we get arithmetic geometric inequality, but with a loss in the constant. You have this 1 over e constant here. So now you can either say, well, I'm fine with that, at least that's something, or maybe there is a way to improve it somehow and recover the stronger inequality from this weaker one. And here is a very, very cheap trick. So you always look at what you have and try to exploit some symmetry. So the arithmetic geometric mean inequality has some underlying symmetries. I'm not talking about symmetries at this point, but let me just pretend that I know what to do, and that somebody told me that it's smarter to apply this weaker inequality to some new numbers, to some new collection of numbers, right? So if I start from non-negative numbers a1 to the an, then actually it might be a good idea to apply this inequality to these numbers instead. So consider all possible products of these numbers, right? Products with, let's say, precisely k terms. K will be determined later. I mean, it won't. We'll maybe consider the limit as k goes to infinity. But all k-fold products make another collection of how many numbers? Well, n to the k numbers, right? That's fine, right? Because there are n choices for the first term, n choices for the second one, all the way to the last one, when you still have n choices. So there is n to the k numbers in total, right? But these have some structure, right? So what is the sum of all those terms? So just very briefly, what do you do? What do you do if you want to sum up all these numbers? Well, use the same trick that you saw on the previous slide. That's pretty much it. I can write this as this multinomial raised to the power n. This, when raised to the n power, picks up precisely all these terms, right? So the sum of these new numbers is precisely the sum of the original numbers raised to the n power. And what about the product? About a product, you want to multiply them all out. Well, then you can just count how many times you see a1 in the product, right? So if I multiply out all these numbers, I'll see a1 in the very first position for any possible choices of the last k minus 1 numbers. And this is going to happen n to the k minus 1 times. But a1 could have been on pretty much any position, right? So it doesn't matter. It will appear any position, so it's actually also to the k power. But the same will hold for any other number, a2, n3, and so on. So the product of all these numbers is going to be just the product of all numbers raised to this power. But then if I want to take the geometric mean, right, I have to take this root, right? And when I do it, the following happens, right? For the geometric mean of these new numbers, I just see the product raised to which power? This power divided by n to the k, so it's going to be k over n. What about the arithmetic mean? Well, this was simple, as I said, right? So you sum up all these numbers and divide by how many of them you have, right? So it's just going to be this, this thing divided by n raised to the power k. And here we are, right? This is what we get down there. Right? Sorry? Oh, right. Sorry about that. There is n terms. There is n terms and a k. Yeah, I'm raising to k power. Okay, and well, that's it. So now you see, I can apply this weaker inequality, and I'm still not any better than I was before. But now the difference is that if I view this as an equality rating the original numbers, then it looks like AMGM inequality again. So it's very natural to take the kth root, and when I take the kth root, this constant here becomes 1 over e to the 1 over k, right? So this is a different constant. I improve the constant. And actually this is small, this is actually larger than just 1 over k. And if I send k to infinity, this will go to 1 over e to the 0, which is 1. So in the limit, you recover the original equality. Well, it's not much, you'll say, it's just AMGM inequality. You could prove it in other ways. But the trick is actually very useful, and actually it makes you think. Since I said that we're going to use some symmetries, I'm not really specific about the symmetry. What is that symmetry that I'm using here? I'll leave it to you for now, and you'll see the answer in Alexander's talk a bit later today. But I don't want to spoil his talk and talk about the algebraic symmetry. Just understand this as a nice idea to plug in some weird things into a weaker form of inequality, play with it to recover the stronger one. But for the rest of the talk, I will always put the symmetry first. I'll explain what is that symmetry that we're trying to explode, and what is the symmetry that's going to help us to prove the inequality. The next example will also be very simple. I'm sure that, of course, you all know Cauchy's inequality. It goes by different names in different settings. But the most, or the original one, the simplest one, the discrete one that considers like n tuples of positive numbers is due to Cauchy, right? So there are many ways of interpreting this inequality. In n-dimensional Euclidean space, the right-hand side looks like some product of norms, and the left-hand side looks like an inner product, and so on. But this is actually a very simple inequality. It also goes, has many quite simple proofs. But let's just pretend we don't know any of them, right? Let's just pretend we don't know any of them, and that we want to start very, very naively, yeah, just with something that comes to our mind first, right? So if I have a sum of such things like AJ, BJ, well, the simplest thing that I could do is to use some elementary inequality that will relate this to the squares of AJ and BJ. Well, this is very simple. Of course, you've seen it already. Well, you can just interpret this as a very, very special case of AMGM inequality, right? So the arithmetic mean of these two squares is greater than or equal to the geometric one, which is the square root of the product. And if the numbers are positive, which can be assumed without loss of generality, if some of them was 0, this term wouldn't appear on the left, then you get just what you want. But even easier than that, you don't need to know anything. This inequality is just equivalent to the square of the difference being non-negative, and it doesn't get any simpler than that, right? So that's probably the simplest inequality of all. Right, but yeah, so what do? We just sum up n such inequalities, and we end up having this inequality to see at the bottom. But this is bad, actually. So in the language of inequalities, you kind of missed, right? Look, I mean, if I use the same trick for the whole sums, I see that the thing that I got on the right-hand side is actually larger than or equal to what I needed to obtain, right? So this is bad. There is no way that I can continue this way and arrive to what I wanted, right? I already went over it. So game over. Not really. Actually, there is a very simple trick that can save the day. So even if you start this naively, you can still save the proof, right? So how? So what is some underlying symmetry that you see in this inequality? Well, it's scaling. You can scale the numbers. What does it even mean? let's say you can multiply all AJs by some factor, right? So replace this AJ by the wiggle arrow with some, let's say, lambda times AJ. This lambda factors out very, very nicely. If you do it for every single AJ, right, this number lambda factors out from the whole sum. Also on the right-hand side, it factors out very, very nicely. Right? Okay. But if I don't want to change inequality, I can simultaneously replace every bj with bj over lambda, right? And this actually won't change the original inequality because the left-hand side stays the same. Each product is still the same. On the right-hand side, lambda factors out from the first term, 1 over lambda factors out from the second one, and it's all fine. So this is the scaling invariance, a certain scaling invariance of the inequality, which is very nice to observe, right? So let's appreciate it even if this in this very simple example. But what about this inequality that we got down there? Is it also scaling invariant? It's not. Is this good or bad? It's actually good for us because we can use it now. So how about applying this new inequality in this new situation, right? Replacing every aj with this lambda aj and every bj with bj over lambda. And here is what you get. So what is actually different now? Well, what is different is that now I can even choose this number lambda however I wish, maybe even depending on the numbers aj and bj, right? So I can maybe optimize at the very end. I can maybe optimize and choose what's the best choice. I can choose lambda so that it minimizes the right-hand side. But I don't even have to be that rigorous. I can even maybe guess, right? So maybe the best guess is to choose lambda that kind of balances out the two terms on the right-hand side. It's very kind of natural, right? To maybe choose lambda in this way, right? That the two terms on the right-hand side are equal, which forces lambda to the fourth to be the quotient of those two sums of squares. But when you take the square root and plug it in back inside, you see that each of the two terms is just 1/2 of the product of those two powers, right? And then when you plug it in up there, you get the original equality. 2 times this guy is just the right-hand side of the Cauchy-Schwarz inequality. So we saved a very bad proof, right? So halfway realized, oh, we're not doing it right, and we saved the day using this very trick. We'll see a bit later, and you see on the materials, this trick actually works out quite nicely in much more difficult settings, right? In many areas of mathematics. But we'll come to that a bit later. So the next example, we'll have some geometry at least to be able to draw some nice pictures. So here is actually a very cute inequality in geometry, even though it could be phrased even more generally when you don't even see anything, right? Only in terms of functions and integrals. But a very cute formulation is the following. It's called the Loomis-Whitney inequality. I don't know if you heard about it, but it's also quite well known. It's quite well old. The paper that actually proved this inequality appeared in the late 1940s. So it's ancient math also, in some sense. But it's still cute and it's still used today. So suppose that you have some body in three-dimensional space, and suppose that it's somehow decent. It's not too ugly in the sense that maybe its boundary surface is, let's say, piecewise smooth or something like that, right? So just think in terms of a ball, of a cube, of a polyhedron, or anything like that, or any perturbation, nice perturbation of those usual bodies that you meet in school, right? So suppose you have some three-dimensional body, and project it on each of the 3 coordinate hyperplanes, right? Project it down to the floor, to this wall, and to that wall over there, right? Okay, or the other one. Doesn't really matter. Doesn't make any difference. So you get two-dimensional shapes, right? So you can compute the volume of the body and the areas of the 3 projections, right? So if V stands for the volume and A for the area, then the following holds. The volume is less than equal to the square root of the product of the areas of these three projections. It's not actually very difficult to prove this inequality, and this power of 1/2 might also hint to some application of Cauchy or Cauchy-Schwarz inequality in some sense. But I'm not actually doing it now. You could do it as an exercise, you'll see. It's not very difficult. But right now, what I actually want to study is, can I maybe generalize this inequality? Right? First, well, what does it mean to generalize? First, can I improve the constant? Obviously, no, because, for instance, this inequality is quite sharp if we take the cube, right? If we take the cube, let's say a unit cube, side 1, right? It certainly has volume 1, and each of these projections also has area 1, right? 1 is less than equal to 1. Okay, that's sharp, right? At least something. Then, of course, you can immediately start thinking, is this the only extremizer, or are there many other bodies? Of course there are. Maybe you figure out all of them, or at least all nice extremizers by the end of this talk, right? But what I want to ask is, there's maybe hope for proving a bit more general inequality, right? Where those areas of projections are taken to some powers alpha, beta, and gamma, right? Is there maybe a more general inequality of this form, right? So what I want to do is actually show you the following trick. Maybe suppose that something is possible, then to reinforce it using symmetries, use this trick that we already saw, and derive a contradiction from that. Maybe that was too much to hope for, right? So can we maybe bootstrap this to something that is impossible, and then, oh, oops, we couldn't do any better than that. Okay. So first, some sanity check. Well, if I raise areas to some strange powers, it looks dangerous. It doesn't look physically meaningful, right? What does it mean to take some area to some power alpha? So some sanity check would be to check the standard units of measurement, right? If this is actual inequality for something in the actual physical space, it should then make sense, right? In the sense that if the volume is measured in cubic meters and the area is measured in square meters, then kind of the units should match on both sides. Otherwise, it's kind of very absurd, and it's not gonna be possible in real life, right? Well, okay, that's possible. And if you do it here, of course, you see that those square meters are taken to the power alpha plus beta plus gamma, and you get a constraint on the exponents. It's not very rigorous, but I'm just saying, even this could be made rigorous, and it makes sense. So, okay, there are some constraints on those exponents, but this is not enough. This is certainly not enough. So maybe we need to exploit those symmetries a bit more. So what are those symmetries that you see that this inequality has? So yeah, so the hint is already in the title, dilations, right? So maybe you can dilate the body. Well, but not only in this way as I'm dilating the cube, making it a bigger cube, or which is pretty much the same as changing the unit of measurement. I'm stretching the meter. No, actually, I can use more symmetries. I can only stretch the body in one direction, let's say in the direction of the x-axis, right? And that's slightly better because it's more restrictive. And there are many stretchings, right? There are more directions. So if I do that, then it's actually not very difficult to see that the volume stretches by the same factor of lambda. You didn't change anything in the other direction. And two of the projections also change. The projection on the floor is also stretched by the same factor of lambda. One projection does not stretch at all, does not change. And the other one also stretches by the same factor, right? When you plug it into inequality, and you apply the hypothetical inequality to the stretched body, you get another one with a strange power of lambda, right? You have a very strange power of lambda that maybe shouldn't be there. Why? Because now I see, oh, well, if I apply this inequality to some prescribed body that I started with and do it for any lambda, I can easily arrive to a contradiction as soon as this exponent that I'm raising this lambda 2 is not 0. So if it's positive, then I let lambda go to 0, and I get 0 on the right-hand side. Oh, but not every body has volume 0, right? If I start with a non-degenerate body, it will have a positive volume, so it's certainly a contradiction. Something like that cannot hold for every single body, right? So very similar, if the exponent is negative, I let this lambda go to infinity, and again I get a 0 on the right-hand side, and that's again a contradiction. If the exponent is 0, lambda to the 0th power is not there. You don't see lambda anymore, so that's okay for now, right? At least it didn't give me any contradiction. But now I remind you that this could have been done in any direction, in the direction of the x-axis, y-axis, and z-axis, right? So you get 3 constraints for the exponent, right? And you solve this system, and you see that the only possible solution is when all exponents are 1/2. So this is the dilation symmetry, and in the materials that we handed out, you'll see much more advanced examples of this dilation symmetry. So for instance, in many areas of math, like PDEs or harmonic analysis, you have some maybe hypothetical range of estimates, a range of certain exponents where the estimates could hold, right? But then you employ those symmetries just to see if you can rule out many of them, right? Just very many of them will become impossible just because of this symmetry, right? Just be very careful which symmetries you actually have in the problem, right? And that's very common. Well, here this wasn't a very difficult example because maybe by now you already figured out which bodies also make this inequality an equality, right? Do you know some other examples that are also good, just like the cube, right? What else is good? Does anyone know? Well, if we're dilating a cube, any rectangular box is also okay, right? That's true. And of course, it could lead to a slightly different proof of the impossibility, right? But that's another thing, right? Okay. So any rectangular box with edges of lines A, B, and C is also okay. Just plug them in, right? It's also fine. On both sides, you just see A, B, C. Use A squared, B squared, C squared, square root of that, and it's okay. But it still goes along the lines of what I was saying, right? You can just say that those boxes are stretched cubes. I again had all those symmetries inside here, even in this very special case. So even those rectangular boxes can rule out all other exponents already. But I just wanted to say that very often, if these were some functions on the n-dimensional space, this dilation trick works quite well. You don't even need to know what the extremizers are, and quite often you don't. Like for many estimates in partial differential equations, you don't really know the extremizers, and you can still play with this trick. Okay. So the next example will be rather short, so I think it will just fit in nicely before the break. So it's not very long. I want to show you some linear algebra, but very, very basic one, and a very, very basic example of a certain trick. So the trick is another symmetry is taking powers, powering things, right? Powering things can sometimes help. So if you played with matrices, then you know that for a complex matrix, you can define quite a few things. And the simplest concept is this concept of eigenvalue. So the eigenvalue is any number lambda for which you can find a non-zero vector x, right? So that e to the x equals lambda to the x. So that actually this x is stretched precisely by the factor of lambda by this matrix A, that x pretty much as a linear operator on, let's say, column vectors, right? But you can define it pretty much just as multiplying a matrix with a vector. Right? And the spectrum of A is the set of all eigenvalues. Well, the question is, can we locate the spectrum? And in numerical linear algebra, they have very many, very nice tricks of somehow estimating the spectrum, because the spectrum of a complex matrix lies in the complex plane, right? And actually, this is a bunch of dots somewhere, right? So how do you actually compute those dots? Well, from this equality, you just see that the matrix A minus lambda I, when applied to the vector x, gives you the 0. And if this happens for some non-zero x, this means that the determinant of A minus lambda I is equal to 0. So this is a polynomial equation, right? So it has n roots if n is the order of the matrix. So it has n solutions. So even though some of them could repeat, so it is at most n points in the complex plane, right? And the spectral radius is an interesting concept. It is the largest distance from the origin to any of these complex numbers, right? So the maximal absolute value of an eigenvalue. Well, this quantity, as written, pretty much kind of hints that we should first compute the spectrum and then compute the maximum. And this is something that is actually very, very hard to compute or even to estimate. On the other hand, there is something that is much easier to estimate. It's the operator norm, right? Or the operator norm of the matrix is the largest factor that the matrix scales unit vectors. So it's the maximum over all unit vectors of the outputs a to the x, and then compute, measure the length of this vector and take the maximum over all unit vectors. It's called the operator norm. So are these two related, or maybe can the latter be used to estimate the former? Well, actually, yes, and there is actually a very simple estimate that is available here, right? A very simple estimate is actually, just remember what an eigenvalue was, right? Take absolute values, and you see the absolute value of lambda is certainly equal to A applied to some unit vector, and then the length of that computed, which is at most the operator norm. So this inequality here is trivial, right? The spectral radius is at most the operator norm, which is a nice inequality, but it's not much. So is it any good? Well, the thing is, it's not particularly good. Just look at this example. If I take an upper triangular matrix of size n times n, and it has only ones above the diagonal and only zeros below the diagonal, then by what I told you, computing the spectrum is easy in this case. You just see the spectrum on the diagonal. You subtract lambda, and this polynomial equation I was talking about just reads 1 minus lambda to the nth power equals 0. So the spectrum is only 1. And then the spectral radius is also 1. Right? On the other hand, what's the operator norm? Well, I'm just even too lazy to compute, but I can immediately see that it's huge, because if I just choose my vector, my unit vector, to be the vector that has only 1 in the last coordinate, then what I get in the output is a column of 1s, right? So the operator norm is at least the length of this vector, which is the square root, and you see n 1s, so this is at least root n, which can be as large as you wish. So actually, this inequality can be very, very bad for large matrices. But can we save the thing? Yes. Apply it to the kth power of the matrix, right? Plug in the kth power of the matrix. Then, then you might wonder, what's the spectral radius of the kth power? But that's actually easy, because the spectrum of the kth power is precisely kth powers of eigenvalues of the original matrix. It's not very difficult to see if you can maybe change the basis to the one where you have eigenvalues on the diagonal, something above the diagonal and zeros below. Then you can pretty much read the eigenvalues off from this representation. Then this becomes obvious. But let's take it for granted for a moment. If that is true, then I just take the kth roots and I get another estimate. I get the spectral radius is less than or equal to operator norm of a to the k and then kth root of that for any k, for I choose the worst case, right? I take the infimum over all case, right? Surprisingly, now that's actually a very good estimate. It's actually even an equality. It's not important right now, but actually equality sign holds, now it's actually equal to, right? But from the matter of estimation, right, it means that if I could afford myself to compute a large power matrix, then actually I would get an inequality. It's a completely different thing that maybe the operator norm of the kth power is not so easy to compute either, right? So it's not the best way of approximating the spectral radius, but I just showed you this trick of applying this weak inequality and a very bad one to the kth power can actually give you the sharp inequality, right? So it's a trick of taking powers that will be continued after the break, and actually it works in so many beautiful situations, like taking powers and taking kth roots and letting this parameter go to infinity can recover quite a few things in other areas of math. So let's have a short break and
Thank you so much, Professor Kovac. Yes, thank you so much for the first part of your splendid presentation. And now I would like to invite everyone for the short break. But also I would like to notify everyone that if you are willing to ask any questions during the presentations, you are more welcome to do so. So you can engage with the presentation along with the professors presenting today. So we are coming back in approximately 20 minutes. I think it's going to be 11:20, so it's a little bit shorter than, because we are a bit delayed. So please, we have prepared some snacks in the next room, along with some refreshments and coffee. So you're most welcome to have some break. Thank you so much.
Okay. Thank you. Very interesting, actually. Not an engineer, but the way you present the things, there are, it's always easy to present the simple things, right? Other guys will have a harder time. But I went through the studies myself.
数学是最赤裸裸的东西，它直接告诉你一个事情的一个现象的本质，背后的本质是什么。
And mathematics is really something that once you understand it, you can see the beauty of it. You can see the kind of creativity. For some things it's like art. If we think about everything which surrounds us, the technology, the laws of physics that describe what happens in nature, we can use them, we can do something with them. We have the technology that we have because there is mathematics. Mathematics has been the way for the human to understand phenomena.
That
数学是最赤裸裸的东西，它直接告诉你一个事情的一个现象的本质，背后的本质是什么。
And mathematics is really something that once you understand it, you can see the beauty of it. You can see the kind of creativity. For some things it's like art. If we think about everything which surrounds us, the technology, the laws of physics that describe what happens in nature, we can use them, we can do something with them. We have the technology that we have because there is mathematics. Mathematics has been the way for the human to understand phenomena.
That, in fact, by now there are, in fact, many parts of mathematics which have become interesting for application. So many more than a few decades ago.
应用往往是一门综合学科，even 在数学里面，你要解决一个应用数学解决问题，不是一个单门的理论数学可以解决，这实际上是一个系统工程。
试一下，
数学的
有没有机会吧？好吧，你试一下，把这 ATT 我调成12。
It's not going to be like 1,000 times better. And but mathematically, as I say, there are many challenges, and I think once we will understand better how AI works, why it works, how to improve it, how to make it more efficient, safer, and everything, this is when we will see a next revolution.
I mean, if you have theory but without practical case, so you find, you kind of lose a sense of purpose. Whereas, here, if you do also the practice but without a good theory, well, you will continue improving.
Hello. Test. 有声吗？有声吗 ？Test. No audio. Test. 出这没法调啊。Test test test. No no audio. Okay okay. Test test. No audio. Oh, I'll try another cable. Test test test. No audio. Test test test. No audio. 啊，喂，博哥，肯定没问题的。你今天接着 phone 没准能有。
Test test. Test test. Test test. Sorry. Test test.
But you want me to wear this one?
You can see the kind of creativity. For some things it's like art.
Yeah. Yeah. Okay, thanks. Uh-huh. Is it better now? Yeah. Do you want me? Okay. Yeah, doesn't matter. They want. No, it doesn't matter if it's visible. Yeah, it's completely fine. Yeah. Okay. Yeah. You need to test. Yeah. Yeah. If you just.
I will confirm that also with you, so thank you.
Yeah. Yeah. Oh, no worries.
So we are at a moment where I think the computational power, it's really at the maximal level, maybe a bit better, but nothing exceptional. It's not going to be like 1,000 times better. And but mathematically, as I say, there are many challenges, and I think once we will understand better how AI works, why it works, how to improve it, how to make it more efficient, safer, and everything, this is when we will see a next revolution.
I mean, if you have theory but without practical case, so you find, you kind of lose a sense of purpose. Whereas, here, if you do also the practice but without a good theory, well, you will continue on improving already known techniques, but you will not do something revolutionary. I mean, of course, you will advance the technology, but basically you will be in the same trend. I mean, we'll just add some new layer of refinement, but it will not be a step forward somehow.
So we think that, of course, when you are a theoretician, you are looking for understanding. But when you are an engineer, you are looking for something which works better. But then there is a miracle that usually when you get better understanding, you become more efficient. So here, what we need is, in some sense, to enrich the amount of mathematical knowledge of the computer scientists we talk with, in order to make them realize that they can try to implement larger schemes.
就比如说是像那个大型语言模型，它里面最基础的模块是 transformer。transformer 实际上基本来说90%以上都是矩阵运算。这些矩阵运算，我们如何给它加速？如果说我们能够加进很多数学的东西，就比如说利用好的矩阵分解、张量分解，利用比较好的核函数的设计，以及利用比较好的那个位置编码的方式，我相信是可以更有效的去加速整个大型语言模型的计算。
Maybe you can slowly go back.
I studied mathematics. I developed new methods for solar physics. And then during conferences, I met people from cardiology. They showed their time series, their measurements, and looked very similar as solar activity. And then this is a way of interdisciplinary. Then we talked with each other and worked with each other. But the important point is each discipline has its own language, specific language. And the problem is that you have to learn, each side has to learn a bit the basic parts, not complete, but basic parts of the language of the others, that we really can communicate, and that a real problem.
比如说可以从黄大年开始，你比如黄大年可以提供一系列的数学的课程，比如说是一些跟那个 AI 相关的数学，或者说跟其他方面，跟研究物理、跟材料、化学都需要不同的数学。从最简单的方程式开始，慢慢一步步的把这个问题给解剖开来，往深的方向走，就看你的兴趣。觉得要有一个好的一个提供知识的平台，我觉得需要形成一个这样的机制。
Okay, thank you, everyone. Now we'll be continuing, and I would like to give the floor to Professor Kovac again. And please remember, when we have breaks and you would like to refresh yourself, use the toilets, the door behind you will be open, and the toilet is straight and on the left side during the breaks. So yeah, please enjoy the second part from Professor Kovac. And yeah.
Thank you, Piotr. So we're back, and we're slowly getting to the more complex examples. And the next one will be complex in every sense of this word. It's going to be from complex analysis, which is quite different from the real analysis if you're more used to thinking in terms of the real valued functions, right? So it turns out that for a function to be complex differentiable or holomorphic, it actually takes a lot more than just to have a derivative in the sense of real analysis. So if a function is a function of a single complex variable, then you're asking for the following limit to exist in the set of complex numbers for every point z from some domain in the complex plane, right? There is some domain in the complex plane. And actually this property means a lot. So one consequence of being complex differentiable or homomorphic is that such functions satisfy something called the maximum modulus principle, which is true for any nice region with a nice boundary, but we can even formulate it for the disk, right? So we have a disk in the plane, and its interior is denoted by k nodes, and its boundary is the boundary of k, it's the boundary circle. Then you can just say that the absolute value of the function at any interior point is at most the absolute value of some value of f at the boundary, or better to say, the maximum on the disk is certainly attained at the boundary of that disk, right? At the boundary circle. Well, in real analysis, well, this is far from being true, because you can cook up many weird functions in the interior that are all very nice, or even zero at the boundary, right? Or if I want to draw it three-dimensionally, if f was only smooth in the real analytic sense, then their graphs could look like this, right? So this would be the disk, right? And the function could have some peaks inside. But it's not possible for complex differentiable function. That's one of the miracles of complex analysis. And of course, even in real analysis, we know it's true for a larger class of functions, the so-called harmonic functions and so on. But let's stick to complex differentiable functions for now. So how do we prove this principle? Well, of course, it depends how you cover complex analysis in your course. But one very nice trick was invented by Edward Landau. And actually, it only uses the central formula of complex analysis called Cauchy's integral formula. So Cauchy's integral formula tells you that actually you can recover interior values of your function from its values on the boundary circle. Right? That's the first miracle of complex analysis. That is certainly not possible in real analysis. And it tells you precisely how you can do that. Right? It tells you that f of z at any interior point is actually equal to the complex integral, so just integrating along the boundary circle. I'm not even defining this precisely, but this is easy to define in complex analysis. And you're integrating what? You're integrating f of a point at the boundary divided by w minus z. There is some weight, some complex weight. And then you multiply by the factor 1 over 2 pi I. Wow, that's the first miracle, right? You see, on the right-hand side, only matters how f is defined at the boundary, right? On the other hand, the left-hand side, you see an interior value. So actually, every interior value of f can be recovered just from the values at the boundary. But let's suppose that this is all that we know from complex analysis. Somebody gave us this formula that actually characterizes holomorphic functions. Can we recover the maximum modulus principle? Well, first we can start very naively. Just use this integral representation to estimate, right? Just put absolute values inside the integral, right? So the absolute value of f of z is at most the absolute value of this integral. So, okay, 1 over 2 pi I just gives you the factor of 1 over 2 pi. And what else? When you take those absolute values inside the integral, you get the absolute value of f of wy, and then you divide by the distance between complex numbers w and z, right? So w is a point that travels along the circle, right? And this absolute value that you see in the denominator is the distance. But this can be as small as you wish if your point is very close to the boundary. And that's very bad, right? So I can, in fact, prove some estimate, but it's not going to be a very strong one. What I can do, at best, is to estimate this denominator from below by the minimal distance, which is something, right? And then, okay, I multiply by the length of this circle, divide by 2 pi, and that's some constant, but now things are so bad that this constant even depends on the point. This is horrible. This doesn't even count as a legitimate estimate, right? Because f of z is estimated with something that depends on z and something else. Useless, right? Okay, but can we still save the day? Can we maybe recover the estimate that we wanted, which is the same one with a constant 1 from this estimate? Now we remember that we're trying to prove this for every single holomorphic function on some region containing our circle, right? So we have a freedom to change the function itself, right? So why not take a positive integer k and apply what we derived to the kth power of the function, right? Just plug it in. Now it's even simpler than for matrices because it's obvious that this power, this exponent k goes out, right? So of course, I didn't say much about the class of holomorphic functions, but the product of two complex analytic functions is again complex analytic, right? So actually, f to the k is again a holomorphic function, and I can imply, in fact, what I derived to the kth power, right? But now things are easy. This k goes out, take the kth root, and again, let k go to infinity. I recover the estimate without a constant, and we're done, right? It's a nice trick. For those of you who still did not cover complex analysis, well, this is a central formula. You can derive quite a few things from Cauchy's integral formula, but there is also some choice, right, how to derive the whole theory. In many books on complex analysis, people have maybe different ways of doing it. Do you prefer expansion into series before some other properties and so on, right? But this is a very cute trick of Edmund Landau. It actually saves the day just by using the symmetry, and the symmetry is just this possibility of taking powers. Right? Okay. The next example is from one of my favorite topics. It's basic probability. So in probability, you quite often need to prove that certain random variables are highly concentrated around their means, or around some certain number, or even around 0. So a quantitative way of saying this is just estimating a certain thing that is called a tail of a distribution, right? So you have a random variable, and you want to say something about the probability of x being large, meaning that in the absolute value it is at least t for some, let's say, large positive real number t, right? So there is a trivial inequality here. It's called Markov's inequality, even though it might go by different names. But there is like a very, very trivial estimate. If you have an expectation of your random variable, then this inequality is actually ready to use, right? So what is an expectation? An expectation is certain, let's say, integral, but you can also define it in a very elementary way. The expected value of random variable pretty much sums or integrates over all possible outcomes multiplied with probabilities of those outcomes, right? This is the most elementary definition, but of course, in for certain distributions, you need to integrate, and things are a bit more complicated. Why does this inequality hold? Well, it's trivial, because on this event, where it happened that the absolute value of x is at least t, there you use that the absolute value of x is at least t. Okay? On the complement, you just use that this is non-negative. That's it. So the expectation is at least this probability times t, and that's pretty much the inequality, right? Just divide by t, and you're done. It's very, very cheap, borderline trivial inequality, but it can be very, very useful in its sharpened forms, right? But what it actually says, it says that for any random variable with finite expectation, right, you have a very trivial tail estimate that the tail decays as, let's say, some unimportant constant times t to the -1, like 1 over t for large t. Or you could phrase it without a constant, just saying that it's big O of 1 over t as t goes to infinity. But that's kind of trivial. For this, you only need the finiteness of the expectation. But if you know a bit more about your random variable, you can have a better decay, right? And a better decay is desirable. You would maybe want to prove that your tail actually decays much faster. So your random variable is, let's say, much better concentrated around 0, right? This can be actually precious, and this is quite often needed in probability, right? So if you assume that the so-called mth moment is finite, or that the expectation of the nth power of x is finite, then you can prove more by, again, by the power trick. It's silly, right? Just apply this Markov's inequality to the mth power of your random variable, but also replace t with 2t to the m, right? Okay, so this is the same inequality. Oh, but now I just realized that these two events are the same, right? Because x is at least t in the absolute value if and only if its nth power is at least t to the m, right? These are the same events, and I very cheaply obtained this tail estimate So if this moment is finite, then I can say a bit more about the tail. It decays like t to the negative m, or I can just write big O of t to the negative m as t goes to infinity. And that's nice, right? Particular cases of these estimates go by other names, right? For instance, if you just take a special case m equals 2, and maybe don't apply this to x, but to the centered version of x, if x is not centered already, right? Then you can prove something like p of x, and as I said, I'm centering it a little bit, and let mu be the expectation, and I just want to see how much a random variable deviates from its expectation. And if I just use this Markov's inequality, I just get expectation of x minus mu raised squared, right, divided by t squared, in the case m equals 2. But the numerator is, of course, called the variance of the random variable, and you got this inequality that goes by the name of Chebyshev's inequality, right? Chebyshev. Its last name is transcribed in different ways, Chebyshev's, but I can write it using Croatian letters, for instance. That was some standard some time ago, but maybe not anymore. Right, okay, but many random variables are actually even better concentrated than that, right? For many random variables, you can do much better, actually. So, for instance, if you have a normal random variable, then we all know that its density is the so-called normal curve, right? Okay. Or the Gaussian. And of course, if you want to estimate the tail, you would have to integrate out its density function from t to infinity, and also symmetrically from negative infinity to t. So then the tail of the, let's say, standard normal random variable is just this integral, 1 over square root of 2 pi. This is standard, this is given, this is prescribed. This is what we call the density of the standard normal variable. And it's not an elementary integral, right? It's an error function. But you already see super exponential decay here, and it's not very hard to see that actually this decays even faster than the exponential function with any base or e to the negative ct for c as large as you wish, right? So in many situations, then you have much better decay. On the other hand, then you might wonder, oh well, then why bother? Maybe for those particular random variables, we just compute the tail, estimate the tail differently. Well, it turns out that in applications, you quite often want to study random variables that are sums of many independent, identically distributed terms, like as for random walks. So those x's could be even like very concrete, like coin tossings, coin flippings, or it could be more complex, right? And you might want to actually impose some rather general condition on those distributions, or maybe, as I will prefer to view it, on the moment conditions on x that will also guarantee some better tail decay, right? Okay, so I just extracted one possibility, and it's actually the following one. It's not widely known, but it's actually very easy, as you'll soon see. So if I take the mth root of the mth moment, it could be called the m norm or the lm norm of the random variable. It's not really important to call it anyhow. But if I, let's say, assume that these numbers grow at most linearly in the power m, then actually I can already say a lot about the tail. Let us see why. The trick is to get to something that we call the exponential moment, and this is why this is called the exponential moment method. Sometimes, of course, there is a shortcut. I can just start by estimating the exponential moment, especially in situations like these. But I just prefer to phrase it from the viewpoint of the variable x. This is, in fact, equivalent. So what is the trick? Let's try to estimate the expectation of e raised to some small epsilon times the absolute value of x. So this number is sometimes called the exponential moment of x, right? Could be. And if I expand the exponential function into the power series, it looks like this. And it turns out to estimate it, I need to have an estimate of each term of this series, and I need to sum up the series in the end. So, well, I just shamelessly plug in this, this condition that I have, right? So that this nth moment is at most c to the nth power times m to the nth power. Plug it in and see what we get. Well, at least for a sufficiently small epsilon, you get something finite, right? So if I impose a condition that epsilon is, let's say, at most 1/2 times c times e, where c is this constant, then I just play with it, rewrite it a little bit, just this inequality. And now we need to know something more about factorials, right? You'll see that this series converges, but not much. The famous Stirling's formula tells you how large they are asymptotically, right? So they essentially grow like m over e to the power m, and even faster than that, which is certainly even better for us, right? It doesn't really matter. But at least they grow roughly like that. So if you choose epsilon like that, this is smaller, right? You still have some extra power, and you still see an exponential decay of these terms. I was not very careful here. Anything strictly less than 1/. CE would be okay, right? So it doesn't really matter. But for sufficiently small epsilon, this is finite. So this exponential moment is finite. So what do we do now? We use our symmetry again, but not for the nth power, but for the exponential function, right? Let's just use this silly Markov's inequality applied to e to the epsilon absolute value of x, right? Very naively. Once again, these two events are the same, right? Well, yeah, sure. I just raised this I just put this in exponent of the exponential function. These two are the same. In the other direction, just take logarithms. This is the same. And you get this inequality. So if this is finite, and we saw that it is sufficient that these moments do not grow too fast, you have much better tail estimate. You have exponentially decaying tail, right? You have O of e to the negative epsilon t as t goes to infinity for some small epsilon. So this is an exponentially decaying tail. It's not a heavy tail, so those tails that decay much more slowly are called heavy tails, but you have very good concentration. You don't have a heavy tail in many situations that appear in practice. All right, and I have just one more example. Finally, we get to one of the favorite areas of Paul Erdős that I mentioned earlier, is graph theory. So in graph theory, you wouldn't maybe expect many symmetries, right? It's not as symmetric as the real line, and then you might actually wonder, what is a good symmetry here? What will be the trick? I mean, what will the trick use? And first, let me formulate the problem. The problem is estimating the number of walks on a graph. So what is a graph? Yeah, that's what you all know much better than me, because in computer science, graphs are, of course, indispensable today, and in any mathematical modeling. So you have a collection of vertices or nodes, and some of them are connected with an edge. So I only study simple undirected graphs, right? So only those graphs are studied here. So a walk on a graph is just any sequence of vertices so that any two consecutive vertices are actually adjacent or connected with an edge. So a walk can repeat edges and it can also repeat vertices. That's completely fine, right? A typical walk, let's say, from vertex A could be, okay, from A I go to B, and then maybe I go to E. If you don't see there's an edge between B and E, and then maybe I go to D, and then maybe to E again, and maybe B, oh well, maybe then to A, and then maybe to B, right? You got the point, right? But what is the length of the walk is the number of edges traveled. So if I see 8 vertices, then I must have traveled 7 edges, right? So the length of this walk is 7. So for small numbers of S, it's easier to list all possible walks of length precisely S, right? If S is 0, then a walk of length 0 is just a vertex. It's any vertex that you see, right? Okay, well, then the number of walks is just the number of vertices, which we, let's say, denote by N, or N of G, depending, of course, on the graph G. What is the number of walks of length precisely 1? Well, you just travel any edge in any direction, right? So just the number of edges multiplied by 2. And let's denote the number of edges by M. But already when S is at least 2, and let's suppose that S is at least 2 to make things non-trivial, then it's actually not so easy to estimate, or not easy to compute or even estimate the number of walks in a particular graph, right? So it might be precious to have some bound, maybe some lower bound on the number of walks. Let's introduce an auxiliary quantity related to the graph, which is called the average degree. Let's write it d bar. It's the average degree, which is pretty much you sum up all degrees of the vertices. And what is the degree? Of course, is the number of edges, right, going through that vertex. So this particular vertex, I don't even know, it's called Vi, has degree 5, right? But then this average degree can be expressed in terms of the numbers of edges and vertices, because the sum of all degrees is certainly the same as the number of edges, just counted twice, right? Because every edge has two endpoints. So it's just 2 times the number of edges divided by the number of vertices, 2m over n, right? And it's actually a very nice result by Erdős and Simonovic from about 40-something years ago, that the number of walks of length S in any graph is always bounded from below by the number of vertices times the average degree raised to the power S. So it's actually a relatively recent result, much more recent than the other results that you saw in previous examples. And it actually has been rediscovered by several mathematicians like Sidorenko in different contexts, right? Maybe they weren't even thinking about walks, but estimating something, some other expressions in analysis. But this is actually very nice and easy to remember, right? Because it makes a lot of sense, right? So then you can imagine that you want to count the number of walks in a very naive way and in a slightly wrong way, but approximately fine. It's just start from some vertex, okay, there is n choices for the initial vertex. And then, okay, then I just choose any edge that I see going from that vertex. But there is d bar edges on the average available at every single moment. Well, on the average, I'll have that many choices where to go. And I have to make S steps. It makes a lot of sense. It's slightly wrong because some vertices will be very bad. They'll have a very low degree. I won't have many choices. On the other hand, some vertices will give you many choices, right? And this kind of cancels out. And on the average, you're fine. But the whole point is in proving that the number of walks is always at least that much. And that's not very easy. It's not immediately clear why you would be always better than the average, right? This average argument, this naive argument, actually gives you a very good and actually a legitimate lower bound for the total number of walks. Why is that the case? So let's prove this result. And actually, it's beautiful that it's not so easy. And it's actually good that it's not so easy, because this makes things interesting. So here is what Erdős and Simonovic actually do. They prove a weaker estimate. A much weaker estimate that you're quite a lot off. You're off by a factor of 4 to the s. Because supposedly this is easier to prove, and that's what we'll argue in a moment, right? So I just want to prove an estimate without this 4 in the denominator, but this will be easier. Okay, it's easier for very straightforward algebraic way, just playing with estimates. I'm not going to bore you too much. But the trick is also the following. Delta is the minimum degree of a vertex in a graph. So the worst vertex that gives you the smallest number of possibilities when you want to go away from it, right? Let's denote it by delta. So there are two cases. First, if this delta is reasonably large, at least d bar over 4, this gives you some freedom. So by the argument that I just mentioned, you always have at least delta options where to go in each single step. So of course you have such an estimate, and since I assumed that this minimum degree is not too small, then I get this estimate. It would be too good to have a case where the minimum degree is at least the average degree. This almost never happens. It only happens when all vertices have the same degree. But that's a very special case. You don't expect this to be that easy, right? You just cannot cover all graphs, right? But this already gives you some freedom, right? This is already a non-trivial case, because the complementary case, when the minimum degree is very small, is not very difficult to handle. So how do you handle the case when there is a vertex with very few edges from it? By the induction, remove it. Remove it and apply the induction hypothesis. You didn't remove a lot because it had a small degree, right? So you'll see the precise estimation in the materials. It's just slightly ugly, but it's not difficult. So you see, if you have an upper bound for delta, delta is less than something, plug it in here, you have a lower bound for this. And then remember what d bar was and plug it in, and remember that s is at least 2. It's actually very easy inequality for the positive integers that will tell you that this is at least maybe not 1, but what we wanted. Sorry about that. Something in the intermediate step was at least 1 times this. Okay. Just playing with inequalities, you see this actually. It's actually straightforward to prove this. If you want me to do it, I can do it, but let's just leave it only if you really want me to sweat a bit on the board with estimation. As I said, it's actually very straightforward. Just plug it in. Remember that d bar is 2m over n. Or immediately m goes out, and just have a simple inequality for n's. Use that s is at least 2. That's all you need. That's it. Okay, so well, suppose that we prove this weaker inequality. What do we do now? What kind of symmetry can we invent in a graph? Like, what do we do? I mean, it doesn't really give you much freedom. No dilations, no scaling. So what is there? Is there some symmetry that I could maybe invent a new graph to which I apply this weaker inequality? Now we have to be slightly inventive. And let's define a so-called Cartesian power of a graph. Wow, it's like some blown-up graph. All right? So it doesn't go by any standard name. We could call it the Cartesian power of a graph, or by other names that we'll mention in later talks. But the set of vertices of a new graph that are called G to the k is the set of k tuples of vertices of the original graph. So now when I know what the vertices are, I can tell which of these vertices are joined with an edge, right? And I prescribe that 2 k tuples are adjacent or joined with an edge if and only if in the corresponding coordinates the vertices are joined with an edge. It's kind of very natural, right? So in some sense, you have like disjoint dynamics in each coordinate, right? Each coordinate, they do something that they would do in the original graph, but you also make k-tuples out of them. So what is the average degree of this new graph? Well, that's actually kind of interesting, but you see, for every vertex, which is a k-tuple of vertices of the original graph, what is the degree of that vertex? Well, clearly, it's the degree of the vertex v1, which is at the first coordinate, times the degree of the second vertex, and so on, right? Precisely because I can find that many tuples that are adjacent. In each coordinate, I just choose one neighbor, right? So that's it. And you have to sum up all these things to get the sum of the degrees and divide by the total number of vertices. But the total number of vertices is, again, n to the k, right? And you get the average degree of g raised to the power k. Okay? So it's actually very relatable to the original graph. What about the walks? How many walks of length s you have in this new graph? This is actually much easier than one would expect. It's the number of walks in the original graph raised to the power k. Why? Because each coordinate just makes a walk by itself, independently of other coordinates. It's that easy. Just join k walks in each coordinate, make a tuple, and you get a walk in this product graph. Okay, now we finally have all quantities computed for the new graph, and plug them inside the inequality that we just derived, the weaker one, applied to the g to the k. This is a power of the quantity from the original graph. This is again the number of vertices in j raised to k. Again, the average degree is also raised to power k, and you can freely take the kth root and do the same thing that we did before. Just let k go to infinity, this ugly constant disappears, and you get what you wanted, right? Now is a very good question. Can you come up with a proof that would actually avoid using this trick, right? The answer is you can, and it's one of the exercises. You can rephrase this very differently in terms of real-valued functions and integrations, and actually in that formulation, this is called Sidorenko's inequality, which is actually even nicer because you have more symmetries and you can come up with a more direct proof. But you can try it on your own. It's suggested in the exercises. Okay, that was actually my last example before the questions. Thank you for your attention, and try some problems on your own. I prepared a practice set of a bit more difficult examples than you've seen here, that you can maybe think about for some time and then try to see if you can solve them using some of these tricks, and full solutions are also available in the end. So I'm looking forward to your questions. Yeah, please let me know.
Thank you, Professor Kovac. So maybe first we'll start with the questions from the audience. Are there any questions for Professor Kovac? Oh, Maciej?
So I wanted to ask, what are some of examples of the problems only solvable by this approach?
Oh, it's very hard to say the problem can be solved only this way, right? You never know. I think there are a few, but I cannot really. Maybe I'll better send you some links. It's not something that I can define on a board in like 5 minutes. It's some of them are, but analysis is actually full of such things. But once again, you never really know. So instead of giving you hard Olympia type problem, or let's say a research problem that can be only solved this way, I'll just say that quite often in harmonic analysis, this tool is used just to rule out some impossible estimates, like in this Loomis-Whitney inequality, in restriction theory to some surfaces like paraboloids. You can write down some inequalities that you would like to see solved, but why even bother trying to solve some inequalities that are not possible? First, you try all the symmetries and to rule out many of them, and then you see that actually some of them are impossible because you could reinforce them and arrive at a contradiction. Also, like Strickard's estimate in PDEs, there is always some range, you know, that if you consider if they're not localized, and then again there is a lot of symmetry that you can do, and so on. So I would more say that at the research level, this is a very standard trick, very standard tool that can at least help you formulate a good question, right? What is the estimate that is actually worth studying? Because most of them are kind of immediately false by those tricks. But I can never say that the problem can be only solved this trick. It's actually a very good trick to know. Sometimes the solution can be simpler this way. Yeah, sometimes like a very recent example is some log convexity of Gowers norms. At least that's something that I saw recently. I think it has a beautiful solution using this. Otherwise, it's kind of ugly. But I can tell you, I can send the link privately. But thank you so much.
Okay, so perhaps one more question from the audience. Is there any? Oh.
So pretty often you know about classical inequalities that, well, in such and such a case, this becomes an equality, and otherwise it is sharp. And obviously, when you use such a method, then you pass to the limit with a parameter, then usually the sharpness is lost. Is there some remedy for that in that method?
Oh, well, the sharpness is not necessarily lost regarding the best constant, but what is lost is the actual extremizer, right? You don't have the extremizer. If you pass to the limit, you never discuss the real extremizer, only something called the near extremizer, right? This is true, and this trick doesn't help in regard with that, of course. But near extremizer is sometimes also worthwhile studying, and also many inequalities are like strict in a certain sense. Equality never holds, but they're asymptotically sharp. Like many inequalities that Burkholder proved, like in the 80s, his famous inequality where he invented the Bellman function approach and the Burkholder's method, how also many people like to call it. Essentially, his inequality is sharp, right? The equality never holds. And to some extent, it's kind of good to know what the near extremizers are. Sometimes you don't really need to know that. But yeah, well, this method won't help with the actual extremizers. That's true, that's for sure. Well, it's not, it doesn't give you everything, of course.
Thank you very much, Professor.
Yes?
There is one question actually coming from online, from our viewer. Mr. Victor Zoga, I can read it for you.
Okay.
Mr. Victor Zoga asked, does this Loomis-Whitty inequality generalize to higher dimensional manifolds?
Oh, it generalizes to everything, to so many things. So just to give some names for the hints. So the first generalization is, or the class of generalization is called Braskamp-Lieb, so that you can search it up more easily. And don't think about the manifolds yet. Think about flat things. Think about a higher dimensional space and some subspaces, right? Integrate along certain subspaces. Or you have a bunch of functions and have a bunch of subspaces, integrate some a product over certain subspaces. So think about those things. And then you can view the original Loomis-Whitty inequality that I actually wrote down. You can write it in the following way. You don't immediately see any geometry here at first. But let's say this is a triple integral, and you want to estimate it with some sizes of the functions, right? So you use something that you would call the Elter norm of the function. And if these are real valued or even positive, that's actually allowed to write. And do the same with G, and the same with H. Well, this is an analytical form of the Loomis-Whitty. and you will recover the original one if those functions are the indicator functions of the projections, right? Just think about it for a moment. You will actually plug in those functions and see how you start bounding the volume on the left-hand side, and you see the areas of the projections on the right-hand side. So this is the first generalization. But after this point, then you can just see that this sits in a three-dimensional space, and you have three hyperplanes, like three subspaces that are two-dimensional. This is generalized to all kinds of subspaces sitting inside a high-dimensional space. But things are not that easy. It's not that always the most obvious inequality holds automatically. You have to impose some conditions. And people have actually characterized in which situations, for which subspaces, well, there is some geometry now, right? This inequality can hold, right? It's not trivial. You cannot even explicitly write this condition, but you can say, oh, it holds if and only if it holds in a very special case. You kind of write a condition for the dimensions of those subspaces. So there is some dimension type condition that actually gives you, but it's not immediate. You have to test it on some other subspaces, and it's quite complicated. No? But people have generalized this, right? So this is the right generalization. Now this generalizes to all dimensions. Instead of coordinate hyperplanes, you have many other spaces. But then this is actually very useful in restriction theory, but maybe not in this form. But then you want to perturb those subspaces a little bit to curve them, and then you get to the manifolds that you were mentioning, right? So there is some perturbed versions of those Brus-complete inequalities, and that's it. But these are the names to look up, Brus-complete, yeah, to find the whole theory behind it, and then there are variants like what I was doing for my PhD theses are like singular variants of that, because these appear in some other settings in mathematics, like you attach a singular kernel and it becomes a singular integral, but it's very far from what we started.
Thank you very much, Professor Kovac. Please give one more round of applause for Professor. It was a splendid presentation. Now we are going to move to the next presentation, but before we do, our technicians will pass the microport microphone to Mattia. So just don't go anywhere. It will be 1 minute. And in the meantime, I will introduce the topic. So next, we will hear about classical constructions and field theory. And the speaker will be Mr. Mattia Kazalicki, professor at the Department of Mathematics, University of Zagreb, specializing in number theory. So basically just maybe 1 minute and we will be ready. Thank you. So yes, please welcome Professor Kazalicki, and please enjoy the second lecture.
Thank you. So I want to raise this. Okay, thank you. Hello, everyone. So this talk is going to be something completely different. So I'm going to talk about some ancient Greece geometrical problems. What's kind of interesting about these problems is that they are kind of completely elementary described, and it's some kind of a construction. In those days, they were trying to do geometry by using only straight edge and the compass. And the interesting thing about this is that it took mathematicians almost 2,000 years to figure out that these problems are really unsolvable. So the goal of my lecture is first to introduce this problem. On slides, I'll talk a little bit about the history, and then I'll try to explain the mathematics behind this argument of impossibility of these constructions. So, I have a problem with this. Oh, no, no, it's. Thank you. So these are the three constructions: doubling the cube, trisecting an angle, and squaring the circle. So I'll focus mostly on the doubling the cube. So what's kind of interesting about this problem is that, and that there were few mathematical problems with this property, is that this problem was really given by God. So it's also called the Delian problem. Delos is the small Cycladic island in Greece. So this is the birthplace of gods Apollo and Artemis. And the story goes, and this was recorded by historian Plutarch, that in it was ancient times, it was a time where Pluto lived, so it was around 240 BC. So the Delians had some trouble, and so as they used to do in that time, they went to the oracle at Delphi, and the oracle told them that they should double the altar of the god Apollo at Delos, and that would solve their problems. So what they first did, they just doubled each side of this altar, but in that way they make altar 8 times larger as it was before. So this didn't work, and problems persisted. So they asked the Plato for help, and what Plato did, I mean, he tried to do this problem, but he couldn't. He didn't say that he couldn't, but he said that, okay, maybe you're not understanding correctly what the God aim was. Maybe it's not just to build this altar, maybe you just have to study geometry. And really, there have been many attempts of proving this or solving this problem. So lots of Greek mathematicians try to do this. Some of them succeeded using methods that are not really allowed. So when we talk about these classical constructions, we mean just constructing using the straight edge and the compass. And there were some constructions using some other mechanical devices. There were some constructions going into 3D, but no one was really able to solve this problem by just using the straight edge and the compass. It took some time. So only in 1837, Pierre Laurent Wansel proved this impossibility of doubling the cube and trisecting the angle with the straight edge and compass. And a little bit later, Ferdinand von Lindemann proved that pi is transcendental, and then it just followed immediately that the squaring of circle is also impossible with the straight edge and compass. For the rest of this talk, I'll try to explain mathematics that it explains why this is not possible. So this mathematics is essentially the field theory. So this is something that you use, that you learn in the algebra course, or if you are learning algebraic number theory. So these are kind of the ideas that come handy solving this problem. So now I will switch to the Blackboard to explain these ideas. Okay, so I can describe quite easily the main idea. So first of all, we want somehow to algebraize the problem. So okay, so we have this plane, which we can identify with R2. And we are allowed to do some constructions. So in these constructions, you always start with a certain set of points. You do some things with the straight edge and compass, and you construct some other points. And somehow you want to have a control over these points that you get in this way. So the first step to do this is to identify the plane with the complex numbers. So now when we are going to talk about points, we are really going to talk about the complex numbers. And so, for example, if you have 2 points, Z1 and Z2, we will denote by L of Z1, Z2, line through these 2 points. Because this is one of the things that you can do when you do this kind of construction. You just choose 2 points and then you draw the line through them. Also, by Z1 and C of Z1 R, we are going to denote the circle centered at Z1 with radius R. Okay, and now we want to formalize this process that we are doing when we are constructing things. So somehow idea is this, not to focus on one particular construction, but to describe all the possible points that we can get by using the straight edge and the ruler. So this definition comes very handy. So it is a recursive definition of constructible points. It kind of describes what we do when we construct objects. So first we have to start with something. So we will start with 2 points, point 0 and point 1. So the origin and the point 1. So this is going to be this initial set of points. Initial set of lines is going to be empty set, and initial set of circles is going to be empty set. And then recursively we construct from already constructed set of points, lines, and circles, we construct new points, new lines, and new circles. So, for example, the lines in n+1 step are those lines that we obtain by drawing the lines through the points that we constructed in the previous set, in the previous step. Similarly, for the circles, the new set of circles are going to be all possible circles that we construct from the previously constructed points. So we can choose randomly center at Z1, and radius is going to be distance between any 2 points that we have already constructed. And finally, points. The new set of points we can obtain in 3 different ways. So first we can intersect lines. So these are going to be points that are intersection of lines from this previous set. Or we can intersect line and the circle. Or there is a third case where we intersect two circles. Okay, so this is the formalization of this process of geometric constructions. So this is what we can do. So in any point in time, we have certain points that we have already constructed. We can choose 2 points, draw the line through them, and we can choose 1 point to some other points and draw a corresponding circle, or we can take intersections on some circle. So this is what we do. And so now our idea is to somehow try to algebraically describe these sets. So ideally, we would like to find some property of these sets that kind of characterize them, and then using this property show that those particular things that we want to construct are not possible because the numbers that we want to construct are not in these sets. So this is a kind of idea. So to illustrate this definition, I will show it on a simple example. So let's see how these sets look in the first step. So the claim is that P1, so these are the points constructible in one step, consists of the following numbers. So -1, 0, 1, 2, and number 1 plus minus I square root of 3 over 2. So how do we do this? So we start with the first step. In the first step, we only have points 0 and 1. Then in the next step, all we can do is just draw the line through these 2 points. Okay. So what about the circles? We have 2 possibilities for the center. So we can take this circle with the radius 1 centered at 0. So this is going to be this circle. Second circle can be centered at 1 of radius 1. So this is the following circle. And then we can look at the intersection of these 2 circles. We'll get these 2 points, and these 2 points precisely are these 2 points. So we see here that now if you also intersect these circles with this line, that we will get the following description of these points. Okay, so now we can make this natural definition. So we will say that the point is constructible if it is the element of one of these Pn sets. If and only if Z is the element of P of n for some n is n. Okay, and now our goal is to describe these constructible points. So that's our question. So how can we characterize and there's a very nice characterization. So I'll just write down this result, and then for the rest of the talk, I'll explain what this theorem is really saying. So a point Z is constructible if and only if Z is the element of certain field. So I will describe later this field, and this field has a name, so it's called the Pythagorean closure of Q. So this kind of gives us an excuse to go a little bit deeper in the field theory. So my idea is to introduce as few definitions and terminology as possible to be able to describe this result and eventually to show that those three constructions are not possible to do. So what now follows is a primer on field theory. So field is the algebraic structure in which you have two operations, let's say addition and multiplication, which satisfy the usual axiom. So when I say field, you can think of rational numbers, complex numbers, real numbers. If you know something about algebraic number theory, so you have algebraic number fields. So generally here we will be dealing with the subfields of C. Of course, there's lots of theory about the fields, but for us, we will just focus on one notion, the notion of degree. And as it turns out, this is more or less what we need to describe this solution. So if you have fields K and L, then we can think of L as the vector space over K. And we denote by this symbol here a dimension of that vector space over K if this dimension is finite. And we call this number then degree of extension. So we say that the field L is the extension of the field K. To give you some example, maybe consider Q adjoint square root of -1. So this is the set of numbers of the form A times BI. So where A and B are rational numbers. So obviously this is a vector space over Q with basis 1 and I. So the dimension is 2. And what is maybe not so obvious, but also very easy to see, is that this set here is really a field. So if you take the two elements of this form and if you multiply them, you still have the element of this form. If you take you can sum the elements of this form, and you have to check just that you also have the inverse defined in this subset here. So this is the example of the extension of the rational numbers of degree 2. A little bit more general, and this is really how you can think of all these fields that will appear in this talk today, is that if you have algebraic number alpha, let's say algebraic integer, every algebraic integer has a minimal polynomial. So since this is algebraic integer, this is the monic polynomial. And now if we have this minimal polynomial, then we can describe extension Q adjoint alpha, so where alpha is this number over here. So this is going to be the smallest field that contains alpha and Q. And it consists of the elements of the form B0 plus B1 times alpha plus Bn minus 1 times alpha n minus 1, where these Bi's are rationals. So you can again check that this really is a field, and it is as a vector space over Q, a vector space of dimension n. So this is a degree n extension. And every field that will appear in these talks, which is a finite extension of Q, is going to be of the following form, Q adjoint of alpha. Okay, and we will need some properties of this degree map. So we have this simple proposition. So if you have three fields, then degree of the extension of L over F is equal to the product of extensions L over K and K over F. I'll just sketch why this is true. So here, if L1 to LR is a basis of this extension over here, and if K1 to Ks is a basis of K over F, then if you multiply all possible possibilities in all possible ways the elements of this basis, it's not hard to prove that the set you obtain in this way is a basis for this large extension L over F. So this is essentially the proof. Since for us we only care about the degree of this extension, and since we're going to observe the towers of field like this, so this result is important to us because it tells us how to connect the degrees of the different extensions. Yeah. It's kind of technical, but very useful. And now we are ready to define a field that I mentioned in the statement of the first theorem. So a Pythagorean closure of Q. This is how we define it, denote it, is the smallest subfield K of C with the following property. So the property is that every element in K, if you take any element in K, then the square root of that element is also going to be in K. So if you want to say in one sentence, what does it mean? It means that each that this field does not have a quadratic extension. So whenever you try to extend this field with the square root of some element from this field, you'll get again something in this field. So you can think of this field as the smallest subfield of C, such that it does not have the quadratic extension. Later we will describe how this field looks, and we will connect it with those constructible numbers that I talked about earlier. Okay, so let's now first describe the structure of this field. So this structure is important because once we know how these fields look, we'll be able to apply this theory to those problems that we're interested in. So here we have the following statement. If you take any element from this field, then there exists a tower of subfields starting with Q. We'll denote this first field L0. So this is the tower. Such that the element alpha is in this last subfield, and each of these extensions is of degree 2. So how do you think about this? So you start with the Q, and then you join to this field the square root of some element of the Q. And then you get this new field L1. And then you join to this L1 the square root of some element in this field, you get L2, and you can repeat this procedure. The claim is that eventually, with the right choice of these extensions, you will get some field that contains this element alpha. Okay, so let's now try to understand what is going on here. So choose this alpha. Maybe before I start, one more piece of notation. So since we're going to have this situation pretty often, we're going to give a name to this tower or to this field. We're going to call this field 2 solvable. So we say is 2 solvable if there exists a tower like this, such that all these extensions are of degree 2. And now the crucial idea is the following. So denote by F the union of all such 2 solvable fields. So we are going to prove 2 things. First, that this union is really a field. And the second is that this field satisfies that the condition from the definition of Pythagorean closure. So let me remind you, so this is the property that we are interested in. As we'll see later that this f really is equal to this Pythagorean closure. Maybe before I do this formal proof of this, maybe I want to say a few things about the intuition. So why do you expect this to be true? So I already said that we think of this Pythagorean closure as a field that does not have a quadratic extension. So in this situation, so if you have a some subfield that is contained in this Pythagorean closure, then if we look at all the towers that we can get from that subfield, and in the process we will get all kinds of these two solvable fields. They all must be contained in the Pythagorean closure, because if some of them were not contained in the Pythagorean closure, it would mean that this Pythagorean closure does not really has some quadratic extension. So in a way, this is the natural thing to do and expect, and we just now have to prove these things carefully to see that this really is a field and that it really has this property. But somehow a priori it is clear that this will be the case. So once we prove this, so this will imply that Pythagorean closure is contained in F, since by the minimality condition, the Pythagorean closure, this is the smallest field that satisfies that condition, and if F contains that condition, then this will follow, and this is what we really need to prove here. Okay, so let's prove that this is the field. So let's take two elements from F. So we want to show that their sum, their product, and the inverse of these elements, that they are all contained in this field, in this set F. So this will make this set a field. From the definition of F, we know that then there exist two solvable fields M and N. Such that alpha is element of M, beta is element on N, and we have towers that describe these two fields. So first tower is M0, M1, MR, which is M, and the second tower is N0, N1, let's call it NS. Okay, so the main claim here is that then their composition so composition of the fields is the smallest field that contains these two fields. So then their composition is also two solvable. since the tower satisfy the definition of two solvability. But if this field Mn is too solvable, it means that then this field is contained in F, since F is the union of all two solvable fields. And if this field is contained in F, it means then that the sum of these elements, which is the element of this field, the product of these elements, and inverse also belong to F, which means that F is a field. And now we have to just check that star property so if we have some alpha in F, we want to prove that the square root of alpha is also in F. But if alpha is in F, then by definition of F, there exists the two solvable field G that contains alpha. But by definition, the field G adjoint square root of alpha is also two solvable. It means that this extension is also contained in F, which means that the square root of alpha is also contained in F. Okay, so this was a little bit technical, but what we now have is a very nice characterization of this Pythagorean closure. So we can think of this Pythagorean closure as something that is contained in the union of all these two solvable fields. Later we will see that this field is precisely equal to the union of these two solvable fields. Okay. How much time do I have? 5 minutes. 5-10 minutes, okay. Okay, I will mention one more technical result that we will need. I mean, the thing is that I try to reduce these technicalities as much as possible, but still you have to do these things. I mean, after all, the result was open for 2000 years, so you have to do something to prove it. So I'll just mention this simple lemma. So I will leave you as an exercise. So if you have three fields, F1, F2, and F3. Fields of algebraic numbers. And we will assume that F1 is quadratic extension of F2. Then, if you look at the composition f1, f3, and f2, f3, this composition is either going to, this degree is either going to be equal to 1 or 2. So another technical result that tells us what happens with the degree when we do these compositions. So this is easy exercise to prove. Okay, and now I'm going back to the main part of the argument. So I'm going back to the theorem 1, in which we are going to connect geometry, those constructible sets, with this Pythagorean field. So let Z be a complex number. So this number is constructible. If and only if Z is the element of this Pythagorean closure of Q. Equivalently, if you take the union of all these constructible sets Pn, the claim is that we should have, as a result, this whole field. So this field gives us a characterization of the points that we can construct. Okay, so let me start with the proof of this result. So we're just going to prove one direction. So we will prove that for each n, P of n is subfield of this Q Pi. Maybe it would be a better idea to continue this after the break. If I have a few more minutes, then I don't want to maybe stop the proof in the middle. So can we just continue it after the break? Yeah? Yeah.
Sorry, we had some. Yes, thank you. The supplies just arrived, so thank you, Professor, so much for the first part, and we are coming back after lunch. So now I would like to invite all of you to have some pizza. We brought all the different varieties. It will be available here in the next room as previously. So please enjoy your time, and we will have some questions most likely after you finish your second part. So thank you very much, and please enjoy your lunchtime now. Thank you.
Thank you.
Možeš naručiti neka pitanja od ovih naših.
Aha.
Ne znam.
Pa dobro.
Je li dobro pitanje?
Aha, ček samo da me razoružaju. So, can you hear him?
Okay. It's okay. Yeah.
数学是最赤裸裸的东西，它直接告诉你一个事情的一个现象的本质背后的本质是什么。
And, you know, mathematics is really something that once you understand it, you can see the beauty of it. You can see the kind of creativity. For some things, it's like art.
Thank you so much. I hope you have a good lunch. And now we will continue with Professor Kazalicki. Yes, classical constructions and field theory part 2. Thank you.
Thank you. So we're now going back to the main result. So recall, Pn denote the set of points that we can construct in n steps. Okay, maybe this. So P of n is a set of points that we can construct in n steps using the straight edge and the ruler. And in this theorem, we are going to connect this set of constructible numbers with the Pythagorean closure of the Q that we discussed in the previous lecture. So this is the main result. So the union of all constructible points, the set of all constructible points, is equal to this Q of Pj. So we'll prove one direction. So we'll prove that P of n is a subset of this set of this field for every n. So we will prove this by induction. So clearly, P0 is, by definition, set of consisting of 0 and 1. So this is the subset of Pythagorean closure. So assume now that P of n is subset of Q of Pj, and then take some point in P of n plus 1. So we want to show that this point here is also an element of this Pythagorean closure. So now this is this main step that connects constructions with the number fields. So basically we have three cases. So in the first case, that point Z is obtained as intersection of two lines. So second case is that Z is intersection of line in the circle. So if you have a circle, so this everything follows from the inductive definition of these constructible sets. And the third case is when Z is intersection of two circles. Okay, so we want to analyze the field in which this Z is located. So we will deal here with this third most difficult case, and the first two cases will be left to the reader. Okay, so to be more specific, assume the following. So we have this Z that is intersection of two circles. So the first circle has center of Z1 and the radius is absolute value of Z2 minus Z3. So this is the distance between 2 points Z2 and Z3. And the second circle is with the center in Z4 with radius distance between Z5 and Z6. So we'll call this number R. We'll call this number S. So from the assumption of induction, we know that these Zi's that appear here are elements of the nth constructible set, which is by the assumption the subspace of Pythagorean closure of Q. And using this assumption, we want to prove that Z is also in this field over here. Okay, so now this is some elementary analytic geometry. So we can write Z, since it's on the circle around Z1, as Z1 plus R times e to the I theta. And also, since Z is on the other circle, we can write it down as Z3 plus, or Z4 plus S times. So here, this theta and phi are some real numbers. Okay, and now we can play with this expression a bit. So if you put this on the other side, we can write Z minus Z1 times Z conjugate minus Z1 conjugate as R square. So just put this on the other side, conjugate, multiply, you'll get R square because this number has a norm 1. Similarly here, for the other circle, Z minus Z4, Z conjugate minus Z4 conjugate is equal to S square. And now we can eliminate Z bar from the first equation. So Z bar is R square over Z minus Z1 plus Z1 bar. And we can then plug it in this equation over here. So what we'll get is going to be some kind of quadratic equation in Z. And if you look at the numbers that you obtain by doing this, these coefficients of this quadratic equation are going to be elements of Pythagorean closure. So it means that if we solve this quadratic equation, in the solution we'll get the square root of something that is in this field over here, and the defining property of this field is that the square root of any element of this field is again in this field. So what this really means is that Z is, as a solution of this quadratic equation, is also going to be element of this Pythagorean closure. So this calculation is really the main insight in this idea of constructing and looking at these towers of fields of degree 2, because here we see that depending on the case in which we are in, either this z is going to stay in the same field almost immediately, let's say in the first case when the z is intersection of two lines, but in this more complicated case when z is intersection of two circles, when you just compute the formula for z, you see again that you get something that's a quadratic extension of coefficients that you had earlier, and then now it makes sense to have this property on this field, that this field does not have any quadratic extension. So immediately it follows that z is the element of this field here. Okay, and one more result that describes in greater detail this Pythagorean closure. So a number alpha belongs to Pythagorean closure if and only if there exists a tower such that each extension in this tower is of degree 2. So in particular, this means that the degree of this alpha, the dimension of this vector field over Q, is going to be the power of 2. And this really gives us a criterion of, very easy criterion of deciding whether the element is not constructible. So then it means that, and I'll write this as a corollary of this theorem, and later I will prove this theorem. So we have this very nice criterion which says that alpha is constructible, then degree of alpha is a power of 2. Notice that we have a much better here description of the constructible numbers. So we precisely know how to describe this Pythagorean closure field. But to prove that something is not constructible, very often, and actually in all those examples that we are going to be interested in, it's just enough to compute the degree of the number that we want to construct and just to observe that that degree is not the power of 2. So essentially this is okay. So now let's go back to this theorem. Let's prove it. So we have two directions. So first, suppose that such tower exists. So we prove by induction that this field from these towers are the element of this Pythagorean closure. Clearly, K0 as equal to Q is the subset of the Pythagorean closure, and if kj plus 1 is quadratic extension of kj, then it means that there is an element beta such that the extension of kj with this beta is equal to this kj plus 1, and this beta is some algebraic number of degree 2. But if you see what really it's written here, so we have some subfield that is contained in the quadratic in this Pythagorean closure, and then we consider some quadratic extension of this subfield. So intuitively we think about this Pythagorean closure as the field that does not have a quadratic extension. So if we extend this from the definition of Q Pj, it will follow that this is also, this whole field is element of Pythagorean closure. Conversely, suppose that alpha is the element of this Pythagorean closure. By previous proposition, we know that there's a tower L0, L1, Ln with alpha element of Ln, and these sub-extensions are of degree 2. So now we are almost done. What we want, we don't want to finish this with this arbitrary Ln. We want to finish with the subfield Q joint of alpha. So it's obvious that we need to intersect all this field with Q joint alpha. So we define Mj as Lj intersection with Q joint alpha, and then since this degree is 1 or 2, we have desired tower. Okay. So to sum this argument up, we now have a complete description of this Pythagorean closure. It's just the union of all two solvable fields. So for every element in this field, we have a tower like this, which ends with the Q joint of alpha. And this also gives us a complete description of the constructible numbers. So now, whatever construction that we are looking at, we just look at the complex number that we want to construct, and we have to decide if this number is the element of this field or not. If it is the element of this field, then this number is constructible. If not, it's not constructible. And the easiest way to check if some number is the element of the field is to look at the degree. So in case that this degree of this number is not the power of 2, we know that this number is not constructible. If the degree is a power of 2, then we don't know really. So it can be constructible or cannot. So we need some other criterion. We have some things to do. But in all those 3 cases, or 4 that we are now going to do, we will see that really the degree is not power of 2. So impossibility of those constructions will follow immediately from this result. Okay, so let me show how is this applied to those classical constructions. Okay, so first we have a theorem about duplication of a cube. A cube cannot be duplicated with straight edge and compass. Okay, so we start with the unit cube, and we want to construct the cube with the volume that is the double the volume of this cube over here. So if this cube has length of the side 1, we want to construct the cube with the side third root of 2. So really, to double the cube, we need to construct this number over here. Or we need to check if this number is constructible or not. So what do you know about this number? So this is algebraic number with the minimal polynomial x cubed minus 2. So when we say that this is the minimal polynomial of this number, this really means that this polynomial is, so that this number is the 0 of this polynomial, and we are also claiming that this polynomial is irreducible, which is not hard to check. And if the minimal polynomial has degree 3, then this means that the degree of extension, or the degree of number alpha, is equal to 3. But 3 is not a power of 2. Which implies that alpha is not constructible. So this is the proof of the 2,000 years old problem here. It's basically one line when you have this theory developed. Yeah. Okay, now let's move to another problem. So this is the intersection of angle. So here the claim is that there exists an angle that cannot be intersected with straight edge and compass. Okay, so here we have to be careful because you can, for example, trisect the angle of 90 degrees. But here we just claim that not every angle can be trisected. And we will prove this by giving a counterexample. So we will show that one particular angle so this is the angle of 120 degrees cannot be trisected. Okay, so how to phrase this in terms of the constructible numbers? So we know that this angle of 120 degrees is constructible. So this means that the number zeta, which is e to the, or we know that this number w, which is e to the 2 pi I over 3, is then constructible. So assume that trisection exists, so this means that the third root of this number here is also constructible. So this means that zeta, which is e to the 2 pi I over 9, is element of Pythagorean closure of Q. Okay, so but now we'll have to do some algebra to figure out the minimal polynomial of this number so that we can compute its degree and then show that its degree is not the power of 2. So we can proceed in the following way. So we define number which is the sum of this zeta and zeta inverse. Since by assumption zeta is in Pythagorean closure, this number is also in Pythagorean closure. And this means that degree of alpha also has to be the power of 2. Okay, and if you now do some computation, so first note that omega square plus omega plus 1 is equal to 0. So it follows that zeta to the 6th plus zeta to the 3rd plus 1 is equal to 0. Which means that zeta to the 3rd plus zeta to the minus 3rd power is equal to minus 1. So we just put minus 1, we just put zeta to the 6th on the other side and divide everything with zeta to the 3rd. So if you go back to alpha, remember that we concluded that degree of alpha must be power of 2. Then we can compute alpha cubed, which is zeta plus zeta inverse cubed. And if we compute now, we'll get zeta to the third plus zeta to the minus third plus 3 zeta plus 3 zeta inverse. And this is nothing, so this is minus 1, this is 3 alpha, so this is equal to 3 alpha minus 1. So we obtained a polynomial whose 0 is alpha, and this polynomial is irreducible, so we obtained the minimal polynomial of alpha. So we need to check. This is irreducible. So in particular, this means that the degree of alpha is 3, and 3 is not the power of 2, so it means that alpha is not constructible. So we obtained contradiction. And the conclusion is that the angle of 120 degrees is not trisectable. Okay, we notice that this is done in the same way as we did the application of the cube. So we observed our geometric problem. We noticed that it is equivalent of constructing a certain algebraic number, and then we just computed the minimal polynomial of that number. Luckily, it's not the power of 2, so we are done. This number is not constructible, so this angle is not trisectable. Okay, the next result is squaring the circle. So squaring the circle is impossible. It's straight edge. And compass. Okay, proof is here again very simple. So we are starting with the unit circle, and we need to construct the square which has the same area as this unit circle. And if you look at the formula for the area of the circle, then you see that what we really need to do is to construct the square root of pi. So this construction is equivalent to constructing of square root of pi. But we know that the pi is not algebraic number, so the square root of pi is not algebraic number, and then we cannot talk about the degree of this square root of pi, so certainly this degree is not the power of 2, and we immediately conclude that this is not impossible. This is not possible. So this is the Lindeman's theorem. So it's transcendental, and we conclude construction is not possible. And I will talk about one more example, one more classical construction. So this construction is construction of the regular heptagon by Gauss. So theorem 7, this construction is not possible. So a regular heptagon cannot be constructed. So the idea of the proof is again the same. So we first observe that construction is equivalent to construction of the central angle. And the central angle is 2 pi over 7. And this is equivalent to constructibility of the number zeta 7, which is e to the 2 pi I over 7. So now the strategy is the same as before. So we have this particular algebraic number that we're interested in, and we need to find the minimal polynomial of this number. So note that polynomial 1 plus x squared plus x to the 6 annihilates this zeta 7. And we can show that this polynomial is irreducible. But this then means that degree of this extension is 6, because this polynomial is of degree 6. But again, 6 is not the power of 2. Which means that zeta of 7 is not constructible. So again, we solved another difficult problem by just simply applying this theory that we developed. Note here that we have something that was a little bit more complicated than before, so we had to somehow determine whether this polynomial is irreducible. And this is something that happens often when you want to apply this method. So first you need to find the algebraic number, and then in order to compute the minimal polynomial of algebraic number, you first have to find some polynomial that annihilates that algebraic number. And then you have to prove that it's irreducible. So there are some criteria that can help you to do this. One of these is the Eisenstein criteria. So let me see how much time do I have. So yeah. Maybe I can just say one more thing. So there are 5 practice problems where you can try to apply this method. And one of these problems is kind of interesting because it gives you criteria when some angle is trisectable. Because here we just proved that this particular angle of 120 degrees is not trisectable. But I'm just going to state this criteria so that you just see it, and then we can finish with this. So let theta be angle such that the tangent of this angle is of the special form. So it's a rational number where this a, b are co-prime integers. And the criterion is following. There are 2 cases. I'll just state the first one. So if a plus b is odd, then the angle theta can be trisected if and only if number a square plus b square is a cube of an integer. So you have this kind of curious looking number theoretic criteria which tells you whether some angle is trisectable or not. So I'll finish with this.
Thank you so much, Professor. And now, do we have any questions from the audience for Professor?
Yes.
Okay, sorry.
If the power of minimal, if the degree of minimal polynomial is a power of 2, are there any universal techniques to decide if the number is not constructible?
So in this case, it's not so easy because then you have to check whether your field is really too soluble. So you need to somehow construct these intermediate fields, each of which is extension of the degree 2 of the previous to get your field. So in that case, you need to analyze further this element alpha. So you need to compute its minimal polynomial, then maybe knowing its Galois group would help you. So you need to do some more work. But yeah, so there are some methods. Yeah. Galois theory is one of them. Yeah.
Thank you so much, Professor. Any more questions from the audience? Oh, Jahor?
Are there some similar results when, for example, we don't have a ruler, but only a compass or something like this?
Oh, you mean only? I don't think you can do much if you have only a compass.
Why? I mean, you can draw a lot of circles, right? And you can get intersections of these circles.
Okay, okay. I didn't really think about it, so. You need a ruler.
At all?
So you're saying that the same numbers are constructible without the ruler?
So you can draw a line basically between 2 points with just compass?
You cannot really draw it, but you can pretend that you have it.
And you can mark all points. Why? Is it easy to show, or it's like?
You do several cases just to.
Okay. So.
Thank you. Perhaps one more question? No? Okay. So thank you so much, Professor. Big applause again for Professor Kazalicki. Yes, and now we will be moving. All's fine. Now we'll be moving to the next topic, which is error correcting codes and the orange packing problem. The speaker will be Professor Dr. Ivan Novak, student at the Department of Algebra and Number Theory, University of Zagreb, specializing in number theory. Just a second, where our technicians will apply the microphone. Thank you, Professor.
Okay, thank you for the introduction. So I'll talk about error correction codes and the orange packing problem. Okay, so let us start with an introductory problem, a combinatorial problem. So suppose you have 31 prisoners on some island, and tomorrow morning the bad guys, the villains, will place heads on their heads, and either they will get a blue hat or a red hat. And they will know everyone else's head color, but not their own. And so once their heads are put in their heads, they can each of them simultaneously either try guessing the color of their heads or just say nothing. And they will be freed if at least one of them guesses correctly and none of them guess wrongly. Okay, so at least one of them has to guess correctly, and none of them are allowed to make a mistake. And so the question is there a strategy that works? Is there a strategy that works with high probability? So of course, you cannot find a strategy that always works, because for every single prisoner, they have a 50% chance of guessing it right? Because they don't have the full information. Whatever they see, it doesn't uniquely determine their head. Okay. But maybe we can do like better than just 50%. So how can you do it in 50%? Well, just pick a prisoner and say, oh, you will just say red all the time. Okay, and that works in 50% of times. And now the question is, can we do better? Can we do even slightly better than 50%, or can we even do much better, close to 100%? Okay, so it may seem that you cannot do better, because if you look at a single prisoner, well, like we said, they only have a 50% chance of guessing correctly. And also, why would you have many prisoners attempt to guess if only one of them is enough to guess correctly? So you might say, oh, well then, 50% is the best you can do. But that intuition is actually not correct, as we'll see. The thing is, each prisoner has, well, 30 out of 31 bits of information available. So maybe they can use that information more efficiently. Okay. So let's just, how do I change the color?
You can change color as long as it's white or red.
So only white or red, okay.
No. If you push it longer, you can change it. Just push it longer.
Okay.
No, right on the pen, on the pen.
On the pen.
On the pen.
Oh, okay. Okay, but now I went.
It's okay, you can write.
Okay. Okay, great. Okay, well, I just wanted to try it out. Okay, so, yeah, this visual depiction of the problem. Okay, so now we'll stop with this problem for now. We'll come back to the solution later. And now we'll start the theory of error correcting codes. So the idea is, well, if you're sending some information through an unstable channel, the information may get damaged. Okay, so how do you fix that? Well, you can add some redundancy to the information, and then the messages become more stable. So that's the main idea, and that allows you to detect the errors or maybe even fix them. Okay. Let us start with some setup. So FQ will be the finite field with Q elements, but you don't need to think about fields. You can just think about binary numbers. So you can just look at binary numbers with component-wise addition, and that's good enough for us. But in general, you can work with a finite field with Q elements. Okay. Or if you can work with integers mod p for some prime number. Okay. Okay, and so we'll look at the set of all n tuples of elements of our finite field, which we'll consider the alphabet. Okay, so we'll look at all the words of length n. Okay, so all n tuples of elements in the field. Okay, and then we can equip this n-dimensional vector space with a metric, with a distance. Okay, and the distance is really simple. So you look at two words, for example. Let's say we have. Let's say we have these two words, and their distance is the number of components on which they differ. Okay, so the distance between these two will be 2. Okay. Okay. And so this is our sort of the set of our possible messages, the set of our words. Okay. And so the basic definition, what is a code? It's really simple. So a code is simply a subset of the set of all n tuples. Okay. Okay. And there are some parameters which we tie with each code. So n will be this exponent, so the length of each word. M will be the size of our code. Okay. D will be, so when you have words, you can look at the distances between them. And the smallest possible distance between two words of your code, well, we call that the minimal distance of the code. Okay. And we denote it by a little d. And Q is just the size of your alphabet, size of your fields. So in this case, Q is 2. Okay. So what's the idea? So suppose that you have, let's say, Alice here and Bob here. Okay, and Alice wants to send a message to Bob through an unstable channel. Okay. So she chooses a code word from a code. So C is like the set of possible messages Alice could send. Okay. And then she sends this code word through some channel, which may be unstable, and some errors may occur. Okay. And Bob receives some other word, Y, and this word maybe isn't inside C anymore, because maybe it got corrupted. Okay, but in any case, this word is in our vector space FQ to the n. Okay, and what does Bob do? How does Bob decode the message? Well, simply he finds the word from the code, which is the closest to the word he received. So he minimizes this distance between the received word and the word from a code. And Bob just interprets the message as this word, x prime. Okay. And our communication was, sorry, yeah?
What if we have many messages with the same distance? So do we interpret all of them, or?
Well, he chooses one, let's say. But it's a good question, yeah. Okay, and then he interprets the message as this x prime. And we succeeded if, well, the message got correctly sent if Bob interpreted it correctly, if x prime equals x. Okay, and we failed otherwise. Okay, so the simplest example, let's say we have only 2 words in our code, so only 5 zeros or 5 ones. Okay, and Alice chooses a word that she sends. Let's say she sends this one. Okay, and then this word may get corrupted, maybe Bob receives something like this. Okay, and then he, well, this one is at a distance 2 from this guy and at a distance 3 from this guy. So he says, okay, she probably meant this. Okay. And so so it was successful. He correctly interpreted. And yeah. And as long as there are at most 2 errors in the process, then he can correctly determine. If there are more than 2, then he cannot do anything. So he can notice, oh, there was an error, but he doesn't know. Well, he will wrongly interpret it. Okay. Okay, we can just shortly look at the parameters. So 5, 2, 5, 2. 5 is the length. 2 is the size of the code. The minimal distance is, well, the distance between these 2, which is 5. And the size of the alphabet is 2 because it's a binary code. Okay. And yeah, like we said, if Bob receives any word that is different from 0, 0, 0, 0 or 1, 1, 1, 1, 1, then he can detect, oh yeah, there was an error. And if there are 2 or fewer errors, then he will correctly identify the message. And so we say that this code can discover 4 or fewer errors, and it can correct 2 or fewer errors. Okay. And so in general, what happens, if you have a code with minimal distance d, then you can discover up to d-1 errors, and you can correct up to d-1 divided by 2 errors. Okay. So why is that? Well, it's not that complicated. So let's say Alice sent the word X, and let Y be the word that Bob received. And so, okay, so X was the word sent, Y was the word received. And so if the word Y is at a distance between 0 and d-1 from X, then Y is certainly not in the code, okay? Because otherwise you would have 2 words in the code which are too close, okay? And Bob can recognize, oh yeah, there was an error. But maybe he doesn't know what type of error, and maybe he cannot correct it. Furthermore, if the distance is at most e, then like you asked, what if there are more words? So if the distance is at most e, then there will be only 1 word at that distance. So only one word that minimizes the distance. Okay, so let's say X is here, Y is here, and the distance between them is at most e. Okay. Well then, since e is less than d over 2, then any other code word from Y will be at the distance greater than e from Y. Okay, and so Bob will know, oh, she meant this one. Okay, that's what we mean when we say the code can correct d-1 over 2 or fewer errors. Okay. Yeah. So what do we want from our code in practice? Well, obviously we want d to be as large as possible because we want to correct more errors. We want m to be as large as possible so that we can send more messages. So m is the size of the code. And we want n to be as small as possible to, well, to increase the size, to decrease the memory, I can say, increase the speed of communication. And these are conflicting. So if you want larger d, then you will have smaller m and stuff like that. And so we can now look at some upper bounds on the size of the code with given parameters. Okay, so the first one is singleton's bound. So if there exists a code with parameters n, m, d, q, then m is at most q to the n minus d plus 1. Okay. You can try proving this yourself. It's not too difficult. Essentially, you do some projections or something. Okay. And another one, which will be maybe more interesting to us, is the so-called sphere packing bound. So the similar statement. So if there exists a code with these parameters, then the size of the code is bounded, well, by this number. So q to the n divided by this sum. And we see e appearing again. So e is the d-1 over 2. And so even the name of the proposition sort of is a clue for how we'll prove it. So maybe before going anywhere, so which one do you think is better of these two? Which one is sharper? Well, not necessarily. Like if n is small compared to q, then the first one is better because this d is like, so it will be q to the n minus d, and this will be sort of like q to the n minus e. But in practice, you will have like n larger and q smaller. So I guess this one is better in practice. Okay. So how do we prove the sphere packing bound? Well, we will pack some spheres, basically. So okay. Okay. I want it. Oh yeah. Okay. Okay, great. So what do? We look at all words in our code. Okay. And around each word, we draw a sphere of radius e. Okay? And the thing is, by what we've seen already, these spheres of radius e around our points will be disjoint. Why would they be disjoint? Well, if there is a point in both in here and in here, let's say this xm, well then this point, oops, what happened? So if you have a point which lies in both of these, then it will be less than equal to e away from this word and less than e away from this word. And so this word and this word would, by triangle inequality, be at most 2e away. But 2e is less than or equal to d minus 1, which is less than d. Okay? And that's impossible because any two code words need to differ by at least d. Okay. So yeah, so these balls are disjoint. And now what remains to do is to, well, just count how many elements are there in each of the balls. Okay. And, well, this is a short counting argument. So if you fix a word and you look at how many words can be at a distance exactly I from your word, well, you need to choose in n choose I ways where the words differ. And then for each position where they do differ, you have q minus 1 choices for the second word. So you get n choose I times q minus 1 to the power of I, and you sum from I going from 0 to e, and you get exactly the number we wanted. Okay. And yeah, where do we get q to the n? Well, q to the n is the size of the entire space, obviously. Okay. Yeah, we can. This is the same picture as here. Okay. Okay. So now so far codes were just any subsets of the n-dimensional vector space fq to the n, but now we want some codes with more structure. So a code over alphabet fq of length n is linear if it's a subspace, like as a vector subspace. Okay, so now we want our code to be closed under addition and closed under multiplication by scalars. Okay. And when you have a linear code, since it's a subspace over a finite field fq, the number of its elements will be a power of q. Okay. So if, for example, if the basis for this code is, if the basis is x1 to xk, then you look at all the combinations of words you can get. Like a typical word in your code looks like this, right? And the alpha I are in fq. And since FQ has Q elements, you get Q to the K options. Okay. So yeah, the dimension, the size of the code is the power of Q, and the logarithm of that size is the dimension of your vector space. Okay. So we don't look at the size, you will look at the dimension. Okay. And so another advantage of linear codes, except from having more algebraic structure, is that it's easy to describe them. Okay. So you don't need to write down all the words that are in your code, you just write down the basis. Okay. Equivalently, what you can do is you can describe them by a matrix, but well, that's the same as giving a basis, so you just write down a matrix whose rows form a basis for your code. Okay. For example, for the simplest example that we had so far, the code. So this is a linear code because, well, it's one-dimensional. It's a one-dimensional linear code. This is the basis. So the generating matrix would just be this one row. Okay. Okay, and not even can you just give a generating matrix. If you possibly permute the coordinates, then you can always find the generating matrix of the form, of the following form. So you have the identity matrix here of size m, where m is your dimension. And then you have some other matrix A. And so what this matrix A is, well, this matrix exactly contains the redundancy that you have. Okay. Here's like all the information, and here's all the redundancy you have. Okay. Why can we get to this form? Well, that's just, I guess, simple linear algebra, just over finite fields instead of over reals or whatever. Okay. Okay, that's one way of describing a linear code, by giving a basis or giving a generating matrix. But another way you can describe a linear code, or another way you can describe a subspace. Okay, let's try it. Okay. So another way you can describe a linear subspace is by finding a matrix which annihilates it. Okay. So if you have a linear code of dimension m, then there's always an n times m times n matrix, such that your vector belongs to a code if and only if the matrix kills it. Okay. And this matrix H is called a parity check matrix of C. Now, why is it called a parity check matrix? I will not go into that, but yeah. Okay. So that's sort of like the implicit way to define your code, while the other one by basis was an explicit way. Okay, and if you have a generating matrix of the form identity redundancy, then the parity check matrix is easy to describe. It's just this one. So this is easy to check. You can just multiply out those two matrices and see that you get a 0. And then since these two are 0, you get exactly what you want. Okay. And now let's go for an example, which may or may not be connected with our problem of Hamming heads. Okay, so what do? Let's fix a positive integer r. And we look at the matrix whose columns are binary representations of numbers 1, 2, 2 to the r minus 1. For example, if r equals 3, you get 0, 0, 1, 0, 1, 0, 0, 1, 1. Okay, take this matrix, and the Hamming code HR will be the code whose parity check matrix is H. Okay, so this will be our matrix H, and HR is the set of all n tuples such that age annihilates them. Okay, and HR is called the binary Hamming code of length 2 to the r minus 1. Okay. And so what you can prove is that this code has minimum distance 3 and dimension, well, 2 to the r minus 1 minus r. Well, it certainly cannot have a larger dimension because no, it certainly cannot have a smaller dimension because it's the zero set of some matrix of size r. Okay, but you can prove that in fact it has exactly the dimension to the r minus 1 minus r. Okay, and the minimum distance being 3, I think that's easy to show. So maybe I should say, when looking at minimum distance of linear code, you don't need to look at all pairs of words and their distances. You can just look at the minimum weight of a word. So minimum weight of a word, the weight of a word is the number of non-zero components. Okay, and if you have two words in your linear code, let's say x and y, then their distance is the same as the distance of x minus 1 from 0. Okay, and this is the weight of the word, x minus 1. So minimum distance, minimum weight is the same thing in linear codes, so it's even easier to calculate that. Okay, and so what you need to just check, if you have a word of weight 2, you need to prove that it doesn't belong to this set. Okay, and that's not that difficult to check. Okay, and now another thing that we can see is Hamming codes in fact achieve equality in the sphere packing bound. So the sphere packing bound was, what was it? So q to the n over sum from 0 to e. So q is 2 now, n is 2 to the power of r minus 1 or whatever, and e equals 1. And when you do this calculation for the Hamming codes, you exactly get equality. So what does that mean combinatorially, this equality that we got? That means that if you look at our spheres, let's say something like this, then every word of the space belongs to a unique sphere. Okay? Because the spheres partition the entire space. Okay, which means that if you have a word that is not a code word, okay, let's say something like this. So you have a word that is not a code word, then it's at a distance at most, well, at a distance exactly 1 from a code word and from a unique code word. So what does that mean? That means that you can flip a unique bit inside that word to get from a non-code word to a code word. Okay. So you can always go from a non-code word to a code word by flipping a unique bit. When I say bit, I mean like a digit or a letter. Okay. And furthermore, we have this matrix H, which is the parity check matrix. And so what happens if we evaluate this parity check matrix on a vector which is not a code word? Okay. So if it's a code word, we know it's 0. Okay. And if it's not a code word, so x not a code word, then x can be written as some code word plus a vector of the form, so there will be 0 somewhere, then there will be 1, and then again zeros. Okay. Why is that? Well, that's because if it's not a code word, it's at a distance 1 from a code word, which means it can be written like this. Okay. And so when you look at age of x, well, this will be age of x0 plus age of, well, x0 transpose, whatever. So there will be a 1 somewhere, and then zeros again. Okay. And what does this mean? Well, this means well, this part will be 0. And this part will be, if you look at how matrices multiply, this will be exactly the binary representation of the bit in which the error happens. Okay. Why is that? Well, the fourth bit here is the binary representation of 4. If the fourth bit is flipped, then what you get by multiplying is exactly this column. Okay. So it's really nice. It's a really nice combinatorial way to interpret what the parity check matrix does to a non-code word. Okay. Okay, this is just the explanation of that. Okay, we said that. Okay, now let's go back to, how much time do I have? I have until 3:30, right? Okay, great. Okay, thanks. Okay, then just enough time to solve the Hamming heads. Okay, so obviously these codes were introduced with the intention of solving the Hamming heads problem. So let's remind ourselves again. So every prisoner only sees 30 bits out of 31, and guessing their head color is equivalent to guessing the entire word, right? Because guessing one bit is the same as guessing the entire word. Okay. Okay, and like I mentioned, so we look at the Hamming code, H5 in this case, and we look at the balls of radius 1 around each code word, and they will partition the entire space. And so when you have a prisoner, so they will either see red or they will see blue. Okay? And from their point of view, they see two different words. Okay. Either when they're red or when they're blue. So they need to guess which one they're in. Okay. And so what might happen is that both of the words they see are not code words. In which case, both the, let's say, red word they see and the blue word, they lie in some different spheres, different balls. Okay. What theoretically might happen, but actually doesn't, is that both of the words they see are code words. Okay. But this cannot happen. Now, there's a spoiler here. This cannot happen because the word they see here and the word they see here, they differ in exactly 1 bit, right? And they cannot both be code words because they're too close together. Okay, they would need to be at least 3 apart. So you cannot have the second case. So we cannot have that both words are code words. You might have that both words are not code words. And finally, you may have the situation where exactly one of the words they see is a code word and the other one isn't. Okay, so in that case, they see. In one case, they see a center of some ball. And in the other case, they see a point that lies here, inside this ball, but not in the center. Okay. And so what do the prisoners do? Well, the idea is sort of you want to, when they're wrong, you want them all to be wrong at the same time. That's sort of the idea. And what we will do is, okay, so we explained there's scenarios 1 and scenario 2 that can happen, right? So either both of the words are not code words or exactly one of them is a code word. Okay, and if the true word is not the code word, okay, then what happens? Then each prisoner will find themselves in scenario number 3. Okay. Why is that? Well, one of these two words will always be a code word, right? Will always be the true word. Okay, and if it's not a code word, then okay, so maybe I should use another color. Maybe green for meaning the true word. Okay. If the true word is not a code word, then what do the different prisoners see? So they all see the green one, which is the true one. Okay, and they see, each of them sees a different fake word. which will be, say, yellow. Okay. And this fake word will be in the same sphere as this one. Okay? And exactly one of them will see the center of this as the fake word. Okay.
Excuse me, can you just please
Yeah.
explain how do you code the things? So you enumerate the prisoners?
Yeah, enumerate them in some way, and then, well, let's just say, oh, this person will be the first bit, this will be the second bit, and so each configuration is just a sequence of zeros and ones.
How can one see the correct code?
Well, they do not see. They see everything but their own head.
Yeah, so
And then they look at the two options. Okay, and let's say we see they see both of them. Okay?
Okay.
And then one of them will be correct, one of them will be wrong. But they all see the correct one, right? And they see different wrong ones. Okay? Does it make sense? So you have a word, like, let's say this is the correct word, 3 bits instead of 31 or whatever. Okay? And so what do the prisoners see? So the first prisoner sees this word and this word. Okay? So the true word and the fake word. The second prisoner will see this word and this word. And the third prisoner will see this word and this word. Okay?
okay, seeing is just
Yeah, it is.
usually one. Okay,
They-
that's what confused me. Okay.
Yeah.
So then seeing is two options.
Yeah, seeing is considering both options, actually, not really seeing. Okay. So yeah. So in the case that the true word is not a code word, then exactly one prisoner will be in the scenario that they see a code word and a non-code word. The non-code word they see is the true word, and the code word they see is the center of the sphere. Okay? And all the other prisoners will see, maybe this is wrong. So these yellows don't live here. They actually live in different spheres. Okay. So one of the prisoners sees these two. This one is the true word, and this one is the false word, but which is a part of the code. In code. Okay? One of the prisoners sees this, and the other prisoners see true word and some fake word from another sphere. Okay. And every other prisoner will see the true word and some other fake word from a different sphere. Okay. And so what's the strategy in this case? Well, the prisoner who sees a code word and a non-code word will guess that this one is true. Okay? And everyone else will abstain from guessing. Okay? So if they see a code word and if a prisoner sees a code word and a non-code word, this means scenario 1. No, wait. If the prisoner sees 2 non-code words, which is scenario 1, then they don't say anything. Okay? And if they see a code word and a non-code word, then they guess that the correct one is a non-code word. Okay? And this strategy works whenever the true word is not a code word, as then we find ourselves in this case, and only the prisoner who ends up here they will guess this one and they will be correct, and the other will just say nothing because their words are in different spheres. Okay. And what happens if the true word is a code word with this strategy? Well, in that case, sort of all the words that they see are in the same sphere, okay, centered around the true word, which is a code word, and everyone will be wrong. Okay. But we don't care how many of them are wrong. We just care whether any of them are correct or wrong. So this means that this strategy works whenever the true word is not a code word. Okay. And so the probability of it winning is 1 over 2 to the power of 5 because of the dimension of the Hamming code. So the probability of them succeeding is 31 over 30. And it's a really interesting exercise to prove that you cannot do it any better. Okay. So it's a really nice exercise. So any other strategy they would come up with would not be better than giving this probability. Okay. So yeah, this is the strategy sketch. So every prisoner looks at the two words, and if they see different possibilities, then they guess that the true word is not the code word. Okay. So maybe now is a good time to stop and have a break.
Thank you very much. So are there any questions, perhaps, from the audience? No, nothing? Oh, okay.
Can you say something about why is this the best strategy?
Well, I was gonna leave it as an exercise, but I can, yeah, it's really nice. So the thing is, the idea is for every, so each prisoner has a 50% chance of guessing when looking at just them, right? Whatever strategy you choose, they only guess correctly in 50% of the cases, right? And so that means that each prisoner is wrong in 50% of the cases. So if you look at if W is the amount of, maybe I should go white. If W is the amount of winning words with your strategy, then for each word in W you need to have a correct guess, right? So for each winning word you need to have at least one correct guess. Okay, and there's the same amount of correct guesses and wrong guesses, right? And for each wrong answer, so let's say this is the set of the winning words and this is the set of the losing words. Okay, so for each word in W, you need to have at least one correct guess, and for each word in L, well, then you have at most 31 wrong guesses. Okay, because when they're wrong, well, at most 31 of them are wrong. And the total amount of correct and wrong guesses is the same. Okay, so that's the idea. Now you just need to combine that to get the equality that W is at most 31 times L. So you get something like this as the, you get a bound of this type, and then since W plus L is a set of all words, then L is at most, well, set of all words divided by 1 over 32, which means you lose in at least 1 over 32 cases. Okay.
Thank you so much. We're still going to have a second part from Ivan. So actually now I would like to invite you for a short break. There's still coffee, some candies. We have still some pizza. So if anybody still feel hungry, please, of course, enjoy. And we'll see each other in 20 minutes. So thank you.
Kod 1/32, da. Jer ti je kod dimenzija 5. 2 na R minus 1 minus R je dimenzija, znači da ti je R kod dimenzija.
Koji klaš H? 5.
Da.
Ukupno imaš 32, što nije
2 na R minus 1. Da, minus 1 je 5 kao dimenzija voda je 5. Dimenzija mu je 2 na 2 i mu je, recimo, na matrica mu je na rada 5. zaključiti na temelju onog što vidi. I onda će, ako nekad kaže nešto, onda će za isti broj slučajeva kad kaže nešto i neće reći točno i da je krivo.
You know, mathematics is really something that once you understand it, you can see the beauty of it. You can see the kind of creativity, something like art.
S tim apstinencijama da to isto vjerojatno. Ne znam, kažem, moram raspisati.
Da. Ma nisam ni ja raspisao do kraja.
Kao, nije mi očito to, kao da kad abstiniraju da je dalje jedno. Malo mi je preprosto.
Da.
If we think about everything which surrounds us, the technology, the laws of physics that describe what happens in nature, we can use them, we can do something with them. We have the technology that we have because there is mathematics. Mathematics has been the way for the human to understand phenomena.
That, in fact, by now there are, in fact, many parts of mathematics which have become interesting for applications. So many more than a few decades ago.
应用往往是一门综合学科 ，even 在数学里面，你要解决一个应用数学解决问题，不是一个单门的理论数学可以解决，这实际上是一个系统工程，数学的系统工程。
So we are at a moment where I think the computational power, it's really at the maximal level, maybe a bit better, but nothing exceptional. It's not going to be like 1,000 times better. And but mathematically, as I say, there are many challenges, and I think once we will understand better how AI works, why it works, how to improve it, how to make it more efficient, safer, and everything, this is when we will see a next revolution.
I mean, if you have theory but without practical case, so you find, you kind of lose a sense of purpose. Whereas, here, if you do also the practice but without a good theory, well, you will continue on improving already known techniques, but you will not do something revolutionary. I mean, of course, you will advance the technology, but basically you will be in the same trend. I mean, we'll just add some new layer of refinement, but it will not be a step forward somehow.
So we think that, of course, when you are a theoretician, you are looking for understanding. But when you are an engineer, you are looking for something which works better. But then there is a miracle that usually when you get better understanding, you become more efficient. So here what we need is, in some sense, to enrich the amount of mathematical knowledge of the computer scientists we talk with, in order to make them realize that they can try to implement larger schemes.
就比如说是像那个大型语言模型，它里面最基础的模块是 transformer。transformer 实际上基本来说90%以上都是矩阵运算。这些矩阵运算我们如何给它加速？如果说我们能够加进很多数学的东西，就比如说利用好的矩阵分解、张量分解，利用比较好的核函数的设计，以及利用比较好的那个位置编码的方式，我相信是可以更有效的去加速整个大型语言模型的计算。
I studied mathematics. I developed new methods for solar physics. And then during conferences, I met people from cardiology. They showed their time series, their measurements, and looked very similar as solar activity. And then this is a way of interdisciplinary. Then we talked with each other and worked with each other. But the important point is each discipline has its own language, specific language. And the problem is that you have to learn, each side has to learn a bit the basic parts, not complete, but basic parts of the language of the others, that we really can communicate and that they can tell what are their real problems.
比如说可以从黄大年开始，比如黄大年可以提供一系列的数学的课程，比如说是一些跟那个 AI 相关的数学，或者说跟其他方面，跟研究物理、跟材料、化学都需要不同的数学。从最简单的方程式开始，慢慢一步步的把这个问题给解剖开来，往深的方向走，就看你的兴趣。觉得要有一个好的一个提供知识的平台，我觉得需要形成一个这样的机制。数学是最赤裸裸的东西，它直接告诉你一个事情的一个现象的本质，背后的本质是什么。
And you know, mathematics is really something that once you understand it, you can see the beauty of it. You can see the kind of creativity. For some things it's like art. If we think about everything which surrounds us, the technology, the laws of physics that describe what happens in nature, we can use them, we can do something with them. We have the technology that we have because there is mathematics. Mathematics has been the way for the human to understand phenomena.
That, in fact, by now there are, in fact, many parts of mathematics which have become interesting for applications. So many more than a few decades ago.
应用往往是一门综合学科 ，even 在数学里面，你要解决一个应用数学解决问题，不是一个单门的理论数学可以解决，这实际上是一个系统工程，数学的系统工程。
So we are at a moment where I think the computational power, it's really at the level, at the maximal level, maybe a bit better, but nothing exceptional. It's not going to be like 1,000 times better. And but mathematically, as I say, there are many challenges, and I think once we will understand better how AI works, why it works, how to improve it, how to make it more efficient, safer, and everything, this is when we will see a next revolution.
I mean, if you have theory but without practical case, so you find, I mean, you kind of lose a sense of purpose. Whereas, and here, if you do also the practice but without a good theory, well, you will continue on improving already known techniques, but you will not do something revolutionary. I mean, of course, you will advance the technology, but basically you will be in the same trend. I mean, we'll just add some new layer of refinement, but it will not be a step forward somehow.
So we think that, of course, when you are a theoretician, you are looking for understanding. But when you are an engineer, you are looking for something which works better. But then there is a miracle that usually when you get better understanding, you become more efficient. So here what we need is, in some sense, to enrich the amount of mathematical knowledge of the computer scientists we talk with, in order to make them realize that they can try to implement larger schemes.
就比如说是像那个大型语言模型，它里面最基础的模块是 transformer。transformer 实际上基本来说90%以上都是矩阵运算。这些矩阵运算我们如何给它加速？如果说我们能够加进很多数学的东西，就比如说利用好的矩阵分解、张量分解，利用比较好的核函数的设计，以及利用比较好的那个位置编码的方式，我相信是可以更有效的去加速整个大型语言模型的计算。
I studied mathematics. I developed new methods for solar physics. And then during conferences, I met people from cardiology. They showed their time series, their measurements, and looked very similar as solar activity. And then this is a way of interdisciplinary. Then we talked with each other and worked with each other. But the important point is each discipline has its own language, specific language. And the problem is that you have to learn, each side has to learn a bit the basic parts, not complete, but basic parts of the language of the others, that we really can communicate and that they can tell what are their real problems.
比如说可以从黄大年开始，比如黄大年可以提供一系列的数学的课程，比如说是一些跟那个 AI 相关的数学，或者说跟其他方面，跟研究物理、跟材料化学都需要不同的数学。从最简单的方程式开始，慢慢一步步的把这个问题给解剖开来，往深的方向走，就看你的兴趣。觉得要有一个好的一个提供知识的平台，我觉得需要形成一个这样的机制。
Okay, thank you very much. We'll be getting into part 2 right now from Ivan, so the floor is yours. Thank you very much.
Thank you. Okay, so we'll start this second part with a short trip to space. So where the error correction code is used in practice. So, well, whenever you want to send some information through unstable channels. And a good example of that is in space. That's a really unstable channel. So for example, we have the Mariner 9 mission in 1971, which was launched with the goal of mapping the surface of Mars. And the mission in the end successfully turned many images and covering 85% of the surface. And the mission concluded 1 year later. Okay, so for example, some of these images are here. So this is, I think this is the Olympus Mons, or whatever it's called, the large mountain on Mars. And this is some crater, I guess. So to ensure the quality of the image transmissions, they used Reed-Miller codes, which we'll see shortly. Okay. Another example is the Voyager program. This was a set of 2 missions, Voyager 1 and Voyager 2, which were launched in 1977 with the purpose to explore first Jupiter and Saturn, then Neptune and Uranus as well. So, fun fact, Voyager 1 is the farthest human-made object from Earth at the moment. And it will be for quite some time as well. And there is a famous picture from Voyager 1, which is a photograph of the Earth from a distance of 6 billion kilometers. This was taken by Voyager 1 in 1990. So as you can see here, there is a pale blue dot here. So apparently this is the Earth.
Is it the Earth or the error in the code?
Maybe this is the prisoner who wrongly guessed red. Maybe that's him. Okay. So yeah, this photograph from such distance would never be possible without error correction codes. Okay. So on Voyager missions, Reed-Miller codes were also used in combination with some other codes, with Golay codes, Reed-Solomon codes, etc. Okay. So now we'll talk about Reed-Miller codes as another example. So what are they? So let's say we fix a positive integer m, and then we'll define a sequence of codes recursively. They will be binary codes as well. So the code RRM will be called the rth order Reed-Miller code of length 2 to the m. Okay, so R0M will be just the trivial code that we already saw, so all zeros or ones. RMM will be the entire space. Okay, and for the intermediate values of R, we use this recursive formula. So you take all the words U, which were in the previous code R minus 1, you write them again on the second set of coordinates, and on the second set of coordinates you add a word from the code R minus 1, M minus 1. Okay. Okay, this is just the definition repeated. We can also express this in terms of generating matrices. So the generative matrix of Rm will be, well, this here corresponds to the vector u here in the definition, and this here corresponds to the vector v in the definition. Okay, so sort of block matrix. Okay, and okay, so what are the dimensions of Reed-Miller codes and what are their parameters? So first of all, Reed-Miller code IM is contained in Reed-Miller code JM for I less than j. This is easy to see by induction, I believe. And the dimension of RRM is the sum of these binomials. This also follows easily, I think, from induction and the fact that, well, the dimension of a linear code is equal to the rank of its generating matrix. Okay, so how do you calculate this? Well, the easiest way is to look at the rank of this matrix. Okay, and the rank here will be, well, I guess the sum of the rank of this part and this part. Okay, and this gives you a recursion, which gives you this formula. That's sort of the idea. Okay, but this was not a very, like, okay, this is a definition of some code, but it's not very, like, natural. So how do you get to Reed-Miller codes in a more natural way? So what you can do is you can look at the set of all polynomials in m variables with coefficient 0 or 1 and total degree at most r. Okay, what does that mean? That means that each such polynomial can be written as so I1 IS x I1 times x I2 times x IS for some s, and we go through all I1 IS, and we go for s between 0 and r. Something like this. And these C's belong to F2, which means they're 0 or 1. Okay, so you look at the set of all such polynomials. So they're linear in each variable, and their total degree is at most r. Okay, and what do? Well, for each such polynomial, let's call it f, what you do is you evaluate the polynomial at all possible 2 to the m points of f2 to the m. So all possible m tuples of zeros and ones. So you evaluate the polynomial. What you get? You get a vector of length 2 to the m. Okay? And you look at the set of all such vectors that you can get from these polynomials, all such vectors which are from these polynomials. And this forms a vector space. So that means it's closed under addition. And it turns out to be isomorphic to the previous description of the Reed-Miller code. Okay, so maybe we can do an example, something like this. Okay, maybe one variable less, one variable fewer. Okay, so what you do, you first evaluate at 0, 0, 0, then you evaluate at 0, 0, 1, etc., and you get a vector. So when you put 0, 0, 0, you get 1. When you take 0, 0, 1, you get 0. When you take, maybe I should write down somewhere a table or something. So 0, 0, 0 gives you 1, right? 0, 0, 1 gives you 0. 0, 1, 0, that gives you, I guess, 1 again. 0, 1, 1 gives you 0 again. And then we have so yeah, you fill out this table, you get a vector. When you get, so this will be 1, this will be 0, this will be 0, and this will be 1. Okay. So you get a vector of 1, 0, 1, 0, 1, 0, 0, 1. Okay. So that's how you go from a, so we now have a way to go from a polynomial of this type to a vector of length 2 to the m. Okay. Yeah, so just to explain why this thing is the same as the previous description. So if you have a polynomial in m variables, which is linear, then you can write it as some part which doesn't have xm and some part which does have it. Okay. And if you do that, then, well, this will be a polynomial of degree at most r in m minus 1 variable, and this will be a polynomial of degree at most r minus 1 in m minus 1 variable. Okay. And if you look at the previous description, you had m minus 1, r minus 1, m minus 1. Okay. So I'll not go into details, but this is how you get this isomorphism formally. Okay. And so what does this give us? So this gives us like another layer of encoding. So what do? We start with a polynomial. Okay. So let's say the polynomial is something we want to send. Okay. The polynomial is something we want. The polynomial is something that we want Bob to discover later. Okay, so what happens? You start with a polynomial, you evaluate it, you get to the vector. And then you send this vector, and then this vector might end up having some errors, but okay. And then the question is, how do you go from this evaluation vector, which might have some errors? So for example, this 0 might turn into 1. This is an example of an error. How do you go back to the starting polynomial? What's the algorithm to do that? Okay. So we have received a noisy word, which means, well, a noisy vector, a vector with some errors. And we want to find a polynomial which produces these values. Okay, and we have at most, well, we calculated d before. So d was 2 to the m minus r, which means that e is 2 to the m minus r minus 1, and then minus 1. Okay, so we can have at most this many errors in order to have any hope of decoding it. Okay, and so what does that mean? What does it mean to find a polynomial? Well, what you need to do is for each separate monomial, which may or may not appear in this sum. So it appears in the sum if this coefficient is 1, and it doesn't appear if the coefficient is 0. And so for each monomial, you sort of want to see, oh, does this monomial appear or not? Okay. Okay, and so what we do is we'll fix a monomial of the largest degree possible that we haven't yet processed. Okay. Let's say this monomial is without loss of generality, x1, x2, xk. Okay. So what do you do? So maybe I should erase something here, but not everything. So we wonder whether this monomial, does this monomial appear in F or not? Okay. And so what do we do? We fix a set of values for the remaining variables which don't appear. Okay. So you have these k variables that appear in your monomial, and you have xk plus 1, xn, no, xm, I guess. Okay, and so you fix them to be a certain combination of zeros and ones. Okay? And then, with these guys fixed, you vary the variables which appear in the monomial. Okay? And you sum them all up. Okay. So let's say we fix these to be alpha 1, alpha m. And what you do is you calculate using the evaluation vector. Okay? So you do not evaluate the polynomial, but you have the evaluation vector with errors. So you use this, we'll write something like this to know that there may be an error. So this will be a sum of 2 to the k things, k plus 1. Okay, sum over all combinations of x1 up to xk. Okay, where this, like I said, this dash means we're not evaluating the polynomial because we don't know the polynomial, but we're looking at the evaluation vector, which may have errors. Okay, and you look at this sum. Okay, we call this the test sum. Okay, and so the thing is, if there are no errors, so if this f with the dash would just be an f, then what happens is that if you look at each monomial separately, and how many times it contributes with 1 to the sum, and how many times it contributes with 0. So it contributes with the 1 exactly when all the variables that appear in the monomial are 1. Okay? And so what you can prove is that for each monomial in your f, for each possible monomial, other than the one that we're looking at, it will be equal to 1 an even amount of times, which means that when you sum them up, the contribution of that polynomial will be 0. Okay, so sort of this is a trick. It's difficult to, like, we would maybe need an example. We will go through an example. So the thing is, by taking these test sums, you sort of isolate this particular monomial. Okay, and there's a combinatorial step here where you need to prove that each other monomial contributes, well, with an even amount of ones, so it's not important. And what you get is, well, you only get the contributions of this guy. And what are contributions of this monomial? Well, if the monomial doesn't appear in f, well, then the contributions will be 0, okay, because it doesn't appear. However, if it does appear, then when will this be equal to 1 in this sum? Well, exactly when all of these xi's from 1 to k are equal to 1. Okay, so this guy will contribute once if it belongs, if it appears in the polynomial, and 0 if it doesn't. Which means that this sum, if there are no errors, this sum will be 1 if monomial appears. Well, I'll write this as an abuse of notation. Okay, so we sort of extracted this polynomial here, this monomial here, okay, by this trick of fixing all the other values. That is if there are no errors. But of course there may be errors. However, how many errors can there be? There can be at most, what did we say, 2 to the m minus r minus 1 errors. Okay? And how many different sums do we have of this type? So we just fixed the remaining variables to be a single value. But we can fix them to be any possible combination of these. And there are 2 to the m minus k possible ways you can fix these variables. Okay? So there are 2 to the m minus k test sums. Okay? And now the thing is, 2 to the m minus k is more than 2 times the possible number of errors. Okay? So if you multiply this possible number of errors by 2, you will get something smaller than 2 to the m minus k. What does that mean? That means that the majority of the test sums will still be okay. Okay, so the majority of the test sums will contain no errors. So what's the algorithm for decoding? Well, if the test sums are 1 in the majority of the cases, then we judge that the monomial appears. If the test sums are 0 in the majority of cases, we judge that it doesn't appear. Okay. And we do this for every monomial separately with another small twist that if it does appear, then we need to subtract it from the rest of the polynomial. Why? Because this trick with extracting one monomial only works when this monomial is of the largest possible degree. Okay, so we need to, if it does appear, we need to subtract it. If it doesn't, then we just don't do anything and we judge that it's 0. Okay, so this is how the decoding process works. And now maybe let's just, so this is very abstract, maybe an example would be good here. So let us take the polynomial 1 plus x3, x4. Okay, considered as a member of the Reed-Miller code 2-4. Okay. So there is at most one error that can occur in this case. We can check. Okay, so what do we need to do? We need to form the vector of evaluations. Which maybe let's just do it like this then, to make it easier for us. So we need a vector of all possible evaluations. So I will look at x1, x2, x3, x4 as a binary number, and I'll write it in this order. So this will be 1 exactly when x3 and x4 are both equal to 1. Which means it will go something like this. So 0, 0, 1, 0. I think something like this. So why is that? Because, well, if you look at the binary number x1, x2, x3, x4, well, x3 and x4 are equal to 1 exactly for those numbers which are 3 modulo 4. So 3, 7, 11, and 15. Okay, so this is our vector of evaluations. And suppose that we have an error here. So this 1 turns into a 0. Okay? And now what does the algorithm tell us? Well, take a monomial. Let's say we take this monomial, x3, x4. So the largest possible degree not yet processed. This is the first one, and it's the largest possible degree because the largest possible degree is 2. And now what do? You fix the values of x1 and x2. And you look at the sums. So what is the sum when x1 equals x2 equals 0? Well, then you sum all possible combinations of x3 and x4. So it will be, in fact, the sum of the first 4 elements. Okay? So the sum will be 0 plus, now I will write 0 with an error, plus 0, which will be 0. Okay? And if x1 is 0, x2 is 1, then we will sum these 4, and we'll get sum 1. Then we have the case x1 is 1, x2 is 0, in which case we sum these 4 and we get the sum 1. And then finally we have if x1 equals x2 equals 1, then again we sum these 4 and we get the sum is 1. Okay, so the sum is 0 in one of the cases and the sum is 1 in 3 of the cases. So our majority test tells us that the monomial appears. Okay. And now you would have to do this for every monomial separately, even those which, well, it's not enough to just do them for the monomials that do appear, because you don't know which monomials appear, right? You need to do it for x1, x2, for example, the same thing. But you do it for every monomial in an order so that you go from those of bigger degree to those of smaller degree, and then finally you get back the polynomial. And now the question is, the nice question you can think about is, what's the complexity of this decoding process? You can try calculating this. Okay. So yeah, that's it for the read Miller codes, I guess. What time is it? Okay, 15 more minutes. Okay, now let's go to another type of codes, so cyclic codes. So we say a linear code is cyclic if whenever you have a word in it and you take a cyclic shift, the cyclic shift will also be in the code. Okay. So cyclic codes are particularly nice because they have an extra algebraic structure. So we can represent a word in a cyclic code as a polynomial, like this. Okay. And then what does it mean to take a cyclic shift? Well, it means multiplying everything by x. And then if you get x to the power of n, then you consider that to be 1, right? Okay. And what does it actually do? So if you know some abstract algebra, this is sort of like multiplying by x, but in the ring fq of x modulo x to the n minus 1, which just essentially means, well, fq with the symbol which when you take the nth power of this symbol, you get 1. Okay. And the cyclic codes are then the same thing as ideals in this ring. So what is an ideal in a ring? So an ideal is a set closed ideal in a ring is a set closed under addition and multiplication by elements of the ring. Elements of the ring. Elements of the ring. So what happens when you multiply by if you multiply by x and it stays in, and then you take sums, the word stays in the code. What does that mean? When you multiply by any polynomial, the word stays in code. That's how you get the ideals. Okay. And now the question is, well, if we wonder what kind of cyclic codes are there, well, it's the same question as asking what kind of ideals are there in this ring. Okay. And what do the ideals look like in this ring? So if you look at the ring of polynomials fq of x, this ring is what we call a principal ideal domain. What does that mean? That means that every ideal is of the form well, you fix your polynomial and you look at all multiples of this polynomial. Okay, this is a principal idea. This is what it means that an ideal is principal. And a ring is a principal ideal domain if every ideal is of this form. Okay. And since our ring R, which is fq of x modulo x to the n minus 1, this is what we call a quotient of fq of x. And since fq of x is a principal ideal domain, so is R. It follows from standard algebra. Okay. That means that every ideal, which means every cyclic code, is generated by a single polynomial f. In fact, not only can you take just f to be one polynomial, you can even take f to be a divisor of the polynomial x to the n minus 1. Okay. So to classify cyclic codes, it in fact suffices to factor the polynomial x to the n minus 1 into irreducible factors, well, into any factors over fq of x. Okay. So we moved from sort of classifying cyclic codes to factoring a polynomial. So something really nice and concrete. Okay. So the question is, how does x to the n minus 1 factor in the ring of polynomials fq of x? Well, first of all, we will assume q and n to be coprime because it makes things easier. So what do we have? So in general, x to the n minus 1 can be written as a product of cyclotomic polynomials. Okay, where phi d is irreducible of degree phi of d, where phi is the Euler-Tauschen function. Okay, and in fact, we know how the cyclotomic polynomials factor in over finite fields. So if you have a finite field fq, then the cyclotomic polynomial phi n factors into phi of n over f irreducible factors, and each irreducible factor has degree f. And what is f? F is the multiplicative order of q modulo n. Okay. So we have a really nice description of how the cyclotomic polynomials factor, which means we have a nice explanation of how x to the n minus 1 factors. Okay, so for example, let us look at the binary cyclic codes of length 23. So x to the 23 minus 1 can be written as, well, x minus 1 times phi 23 of x. And now what do you need to do? We're looking over f2. So we need to look at the multiplicative order of 2 modulo 23. So which power of 2 is congruent to 1 mod 23? It turns out to be 2 to the power of 11. And so what does that mean? That means that the polynomial phi 23 factors as a product of, well, let's say g of x, h of x, and these are both of degree 11. Okay. And, well, one of these factors gives what we call the Golay code G23. But yeah, in fact, so not only do we have, like, we now have a completely explicit description once we calculate this G and H, we have a completely explicit description of binary cyclic codes of length 23. Just look at all the possible divisors of phi 23 or x to the 23 minus 1, and we know them. Okay. What you can now try is to find what are the possible dimensions of binary cyclic codes of length 23. Well, you need to look at how dimension corresponds to to the degree of the defining polynomial. But that's not difficult to see. Okay. And now we don't have a lot of time, so this will be really quick. We go back to the sphere packing. So far we only used sphere packing sort of abstractly in some abstract metric space and some abstract spheres, but you can ask yourself what is the most efficient way to pack spheres inside the Euclidean space. Okay. So just a small definition. So a lattice in Rn just means, well, this is maybe more complicated than it should be. So you take, so how do you get a lattice? You take n linearly independent vectors, and you look at all the possible combinations you get by taking integer coefficients in front of them. Okay. So what is a sphere packing? So sphere packing of radius r in the Euclidean space Rn is a collection of spheres of radius r such that the distance between the centers of any two spheres is at least 2r. Or in other words, such that the spheres do not intersect except maybe at the borders. Okay. And the sphere packing is called a lattice packing if the centers of spheres form a lattice. So lattice packings are really regular. Okay, so they're just come from lattices. Okay, and so how do we define how densely our spheres pack the space? Well, you look at the volume that the sphere packing takes, but taken inside the big ball of radius r. Okay, and divide by the volume of this big ball you took, and then you take the limit as r goes to infinity. Well, you need to take the limits up because maybe the limit doesn't exist. But yeah, essentially this is what you intuitively think. So sort of the density of how well you packed your spheres. Okay. And so yeah, the sphere packing problem asks what is the largest possible upper density of a sphere packing in Rn. And that number is called the optimal packing density. And so interestingly, the sphere packing problem is solved only in dimensions 1, 2, 3, 8, and 24. And it's open in all others. Okay, so n equals 1 is trivial, n equals 2 is well known since the 19th century. N equals 3 was also solved, I guess, in the late 20th century by Thomas Hales. But yeah, 1, 2, 3 you would expect on this list. But now, why is the next number not 4? Why is it 8 and 24? So these cases were solved by Vyazovska in 2016. So why 8 and 24? Well, because there are particularly nice lattices in dimension 8 and dimension 24 with huge symmetry groups and so on. We do not have time to go into details. Okay, so now let's just, when you have a lattice packing, it's easy to see that the density is the same as, well, it's volume of the unit sphere, or unit ball, I guess, and divided by the determinant of the lattice. Okay, what is the determinant of the lattice? That's sort of like the density of the set of points, I guess. That's something that's easy to calculate when you have a lattice. Okay, and to find an optimal lattice packing, you need to minimize the determinant of a lattice. Okay, so how do we go from codes to lattices? What is the connection? So when you have a binary code of length n, what you can do is, well, you can look at all the points in, well, this should maybe be z to the n, but I guess it's the same. So you look at all the vectors in z to the n, such that when they reduce modulo 2, they belong to your code. Okay, and you take all of these, and this gives you a lattice. And we'll see that the optimal lattice in 24 dimensions, well, we'll not see because we'll not prove it, but the optimal lattice in 24 dimensions will essentially be lattice corresponding to some nice code C. Okay, so what will this code C be? Well, we defined the Golay code to be the binary cyclic code of length energy defined by this polynomial. It doesn't matter what the polynomial is. So its dimension is 12. We can find its basis. We can determine the minimal distance to be 7. Well, although determining the minimal distance to be 7 is not that trivial for this code. It's not that easy to prove that. Okay, and now what you do with this code, so this is in 23 dimensions. So what you can do is you can extend the code by adding sort of a parity check final coordinate. So you add the 24th coordinate, which will be the sum of all previous coordinates, modulo 2. Okay, and then you get something in 24 dimensions, which has, well, still dimension is 12, and the minimum distance is now 8. It is an even code, every word, which means that every word has sum of coordinates 0 mod 2. Okay. And so what is the Leech lattice? The Leech lattice is the lattice which gives the optimal packing in 24 dimensions. And it is essentially the lattice corresponding to this code up to some tweaks and some scaling. So you do not really take the lattice corresponding to this code, but almost. So you take something like this. So all coordinates in vector in the Leech lattice need to be congruent to the same value modulo 2. Let m be that value. The sum of the components needs to be 4m modulo 8, where m is the value from 1. And this second condition says, so when you take a vector in f2 of 24, so you sort of, so you look at the positions. So you have your vector in Z24, and you look at all the coordinates for which the values are the same modulo 4. And you look at the corresponding word in F2 to the 24, and this word that you get in F2 24 needs to belong to your code G24. Okay, this not a lot of time to explain this. I'll just going too quickly to this maybe. But yeah, and this gives the Leech lattice once you normalize by dividing by 1 over square root of 8. Okay. And you can calculate that the density is in fact equal to the volume of the unit sphere, which is this number. So Conway and Sloan have proven in the 1970s that the Leech lattice gives the optimal lattice packing in 24 dimensions. But what's difficult is, the difficult part is to prove that it's also an optimal sphere packing. So there is no reason a priori why an optimal sphere packing would be a lattice packing. But Vyazovska proved in 2016 that the lattice sphere packing generated by the Leech lattice is indeed the optimal sphere packing. Okay, that's it. So thank you.
Thank you very much, Ivan. So now it was a second part, actually, for Ivan's today's presentation. So perhaps after the second part, we have some more questions regarding the presentation. Oh, yes, Kostya?
Hi, thanks for the lecture. And you described the cyclic codes as a very generic family of codes. Mm-hmm. And then you showed us like a very particular construction with very specific application. And I would like to ask you about other applications, because from this, I don't see like a clear picture of why we even want to look at this cyclic codes and not just Golay codes in specifically. Like, what else can we do with cyclic codes?
So, the good thing about cyclic codes is they have a lot of they have extra algebraic properties, right? They have this nice property that you can only define them by one piece of information, for example. You only need one polynomial to define the cyclic code, while for a linear code, you need the basis. Right? Mm-hmm. So you need less information to define them, and they have some nice properties. And I guess that would be the reason why you look at them, because.
Are they applied outside of theoretical proofs? Like, can you use them actually for transferring information?
I think so, yeah. You should be. Well, I'm not an expert on the practical side, but I think they are used, yes.
I see. Thanks.
Thank you. Perhaps any more questions from the audience? Oh, okay.
So how do you compute minimal distance in, let's say, Goa code, all those cyclic codes? Yeah?
The minimal distance of a cyclic code. So there's a, well, I can write down the result. It's difficult in general. well, I don't want to say something wrong, but I think it's yeah, I think it's NP hard even, and I'm not sure, but there is a nice like sufficient condition. So when you have a cyclic code, it's a divisor. Okay, it's defined by a divisor of x to the n minus 1, right? And what you can do is you can look at, okay, take alpha to be a primitive nth root of unity, okay? And then you look at you look at these, and the set of roots of f will be a subset of this set, right? And you can look at these exponents. Okay, let's say f equals something like this. Okay, and then what you can do is, well, f is uniquely, well, the code is uniquely determined by this set of exponents, right? And then you can look for consecutive elements in this set. Okay, so the theorem says if there are delta consecutive elements in this set, the minimal distance is at least delta plus 1. Okay, so something like this, but it's not. This is only like a sufficient condition for the distance to be this. This is not an equivalence.
Okay, thank you so much. So if there are no more, Kostya, yes, some additional, please.
A kind of a small follow-up to this question. So one advantage to these codes that I see is that if our number has a lot of factors, we could kind of like pick the polynomial to have a degree with like it seems like we have a lot of control over whether we want to prioritize like how many errors we can afford or how much information we can store for a fixed size of word. So I was wondering if I just take some n and then just take a random polynomial, is there any guarantee that it will be decent?
No, there's not. In fact, for example, what can happen is, I don't know, let's go to n equals 9. Okay, and then you can take this polynomial. Okay, and you think, oh good, this should have minimal weight, minimal distance 3, right? Because it's defined by this guy, which has weight 3. But you can see that this guy contains the word of weight 2. So yeah, if you take something random, then it might happen that the generator has bigger weight than some other words in the code, and you get small minimal distance. So you got minimal distance of 2 here, even though you sort of expected 3 by taking a generator. I don't know if that explains, but yeah, if you take a random polynomial, you will not get really lucky. So what you can do is you can use this, okay? And what you do is, okay, well, if there are delta consecutive elements, then I know something about my minimal distance. So let me build a polynomial which has delta consecutive elements. So that's how you would construct a cyclic code that has good properties, by looking at this set and picking the appropriate exponents that you want.
Thanks.
Thank you. Okay, thank you so much, Ivan, for your presentations and your great topic. So actually today we are reaching the end of the first day, and the last presentation for today will be from Dr. Alexander Bull, senior, as perhaps I didn't read it properly, I'm sorry, is a senior research assistant at the Department of Probability Theory and Mathematical Statistics, University of Zagreb, specializing in harmonic analysis. Alexander is receiving the portable microphone right now, and he will join us on the stage in a second. It will be the first of 2 parts, and the second part we will have tomorrow morning. So the floor is yours. Yes, the pointer, right? There it is.
Yeah. It's not. Oh, what? Okay. Hi. I hope you are not too tired to listen to another talk. I'll try to be concise and short as possible. But for today, we will just introduce the tensor product. How many of you have already seen tensor products in your work? Okay, great. It's very applicable in computer science, so many of you probably did something with tensor products. It's used in, I don't know, machine learning. There are a lot of compression things with tensor products. So I would like to introduce tensor products first in a very concrete way, try to solve some basic problems, and then to actually motivate the tensor products. And then we will see in the second part tomorrow the broad spectrum of applications of tensor product structure. So for the first slide, I made a little typo when I was preparing these slides. Did everyone hear about bilinear forms? These are just, do you know what the dot product is? It's standard thing to work with, right? And multilinear form is just a function which takes n vectors and it's linear in each coordinate. Okay, this is a multilinear form. So bilinear form is, for example, dot product of 2 vectors, right? This is a bilinear form. We can have a multilinear form. We can take n vectors and we do something in a way that it's linear in each variable. So the basic question is the following. Suppose we take a standard basis for R2. Let's take the simplest example, and we will see that it already is not clear when do we have an answer. I will write this problem. So suppose that we have a bilinear form which satisfies that. So this is E1. This is equal to some number, B of 0, 1, 0, 1 is equal to some other number. And I will just write it in a correct way. There is a little typo here in the second one. So 1, 1, 1, 1 equals to C3. And B of 1, 1 and 1, 2 equals to C4. I give you some numbers. For example, C1 is 1, this is 2, this is 3, this is 4. Can you find some bilinear function that satisfies these conditions? This is like a very natural question. Does anyone know the answer? Is it possible? Not possible? Okay, that's great. Then you'll learn something. But if I change the last condition just in a simple way, that instead of looking at 1.2, I will change this condition to B of 1, 1 and 1 minus 1, 1 minus 1. What if I define this to be C4? Let's say 4. So if this is equal to 4, can we now solve this problem? So these two problems look similar. The coefficients look pretty arbitrary. I can write any conditions, and I want to know if there is some bilinear form which satisfies this. And I can only use linearity in each variable separately. So it's not a very simple question to answer immediately if you haven't seen the resolution of this problem. So you can think about it for a while we go to the next topic. And obviously, the next question is, what if I have a trilinear form, multilinear form, how to solve analogous problems for multilinear forms. And we want to have some tool that can always be applied. Ideally, what we know how to solve, like that's probably the only very clear part of mathematics, is linear algebra. In linear algebra, we know when we can solve things and when we cannot. We know we have a Gaussian elimination process, and if it brings us to something, then we know how to solve it, right? So we would like to transfer this problem, which is multilinear, to a linear problem. Okay, this sounds reasonable, right? Okay, so let's study bilinear forms. I'll take another board. Let's start bilinear forms, for example. This is like the basic thing that we want to understand. So if you have a bilinear form, this means both of variables are linear. And we know that if something is linear, if you have a linear function of a vector, so if you have a function that satisfies alpha u plus beta v equals alpha times f of u plus beta times f of v, and f is from r to power of n to r, then we know that f of u can be written as some vector multiplied by u, or maybe the way you write it in computer science, if we consider 1 times 1 matrices as numbers, then we can write it as transpose times u. This is something that you probably learned in linear algebra course. In the first linear algebra course, it's called Riesz representation. You have a vector, and each linear function can be expressed in this way. Okay, so if we just look at the linearity in the second variable, then we can find, for each u, we can find some vector a of u that is linear in second variable. Now, if we study this a of u, then if we study linearity in the first variable, then we just write conditions and insert some specific value of v. I won't bother you with this. You get that this a is actually a linear operator. This is like a simple problem. You can see the notes, or you can try it on your own. It's a very simple linear algebra problem. So what we actually found is that every bilinear form can be written as follows. So each bilinear form can be written as, this is a dot product. I'm not sure it's working though. This is a dot product version. You saw this before, right? So each bilinear form can be written as V transpose times A times U, where A is some matrix. Let's say that U and V are elements of R to the power of n. So these are vectors, and this is a matrix, right? So each bilinear form can be written this way. And now if we just push this notation to limits, we want to observe that we can write this product. We would like to, so we have two parameters. We multiply matrix from each side. So this obviously cannot be generalized to 3 vectors. Okay, so if we have 3 vectors, we cannot multiply matrix from above or something else. We have to find a way to write this as a matrix times some vector, right? And this is appropriate notation. So if you expand this form, then you see that if you have a matrix, then this matrix, how you multiply matrices, obviously you multiply this row with this column, and then you take also multiply it with this row. So we have forms like this, and when you check the matrix multiplication, you can see that this can be written as follows. I will just write it this way. So this is the first column. Sorry, A1 is a first column, A1 up to AN, and this is U1 up to UN, and this is V1 up to Vn. And when you just expand things, you can see that this is equal to AN transpose that acts on such weird vector in which we take U1 and multiply it by vector V, and take U2, multiply it by vector V, and go up to UN and multiply by vector V, right? This is the block matrix notation. If you do some computations with computers, then you probably saw this, but this actually means that you take a huge vector which is U1 and then multiply V1 up to Vn, and you take U2, multiply by V1 up to Vn, and go up to Un multiplied by V1 times Vn. Okay, now this looks awfully complex, right? But this can be easily generalized. So what did we gain by using this notation? So we have some weird combination. So now this has size n squared if we have vectors from the same vector space. In general, it can be m times n. We do not need to have the same vector space. We can have m times n. So we have a lot more vectors. But now we can see that bilinear form is just a one matrix multiplication on this weird vector. Okay, and we are reduced to some kind of linear algebra, right? This is our gain. So we form this weird vector, and we are reduced to the linear algebra problem. Okay, everything fine. So this is the actual gain that we got here. So now I want to have this written somewhere aside. So we are motivated by this, and we define Kronecker product of two matrices in the following way. We just generalize what we did now. So Kronecker product of two matrices is the matrix that looks exactly like the one we had with vectors, just we can use the same A1n times B, A(n)(1) times B, and A(n)(n) times B. Say this. Sorry, Mn. We can have we can have different dimensions. We don't care. We can define Kronecker product for any dimensions of matrices. This is not a classical multiplication of matrices, so this can be M, this can be N. Okay, so this is the definition of Kronecker product. Let's take some simple example to see what it looks like. So we take a matrix 1, 1, 0, 1, and we multiply it with, I don't know, 1, 1, 1, 1. Okay, let's see. This is a very, very simple example. So what do? We take the first one, and now we'll have a matrix which is of size, so we get used to this notation. We take this number 1, we multiply the whole matrix, so we will have 4 1s here. Maybe I could have changed this 1 to 2 so we can distinguish some numbers here. Let's write it like this, and I can delete this, so this will be right 1, 1, 1, 2. The same matrix will be here. Now this is 0, so everything is multiplied by 0, and this is just doubled 2, 2, 2, 4. Okay, and now we have a 4 times 4 matrix, which is the Kronecker product of 2 by 2 matrices. Okay, this looks a little bit weird. This is what you think the matrix multiplication should look like multiply each 2 indices and you get something. And it's weird, but it's very useful. Okay, now have this in mind, and we will see the basic properties of this matrix multiplication. So what do we have? I don't want to write all these properties. Yes.
Shouldn't the first matrix be 1, 1, 0, 2 instead of 1?
Yeah. Sorry. I missed. Thank you very much. This is the same, right? Sorry. I changed it in. So this will be the same 1, 1, 1, 2. Thank you very much. Somebody's following. Great. So this is the Kronecker product of 2 matrices. Thank you. And now if you check the properties of this Kronecker product, you can do it this evening if you are very eager to do that, but you can trust me that these things do hold. So if we have 2 matrices, A and B of the same size, then we can multiply it by C, and this will be the same as multiplication of A and C and B and C. Right, so this is linear in the first coordinate. Okay, so whenever these expressions are defined, this will be true. Okay, so this is defined only when A and B have the same size, and when they have the same size, this is true. Also in the second coordinate, and this is a 0 matrix of arbitrary size, and this 0 is a matrix of size with appropriate size. Okay, so we see that it has really nice properties, something like bilinear forms. Right, it's linear in first coordinate, it's linear in second coordinate. That's great, that's exactly what we wanted. Also, we can see that if we take a basic matrices that have 0, 1, 0, 0, so these are like 1, 0, 0, 0, also 0, 0, 1, 0, and what is the last one, 0, 0, 0, 1. Okay, this is the basis for matrices of size 2 times 2. Then if we take these 2 bases, this will be, and multiply the Kronecker product, we will get, by multiplying these matrices each with another, we will get all the matrices of 4 times 4 that are all 0 except from some 1 at some point. Okay, so this is 4 times 4 matrix when we multiply these two matrices. So this will again be a basis for this vector space of 4 times 4 matrices. Okay, so this has really nice representation. Furthermore, we can concatenate these Kronecker products, and this is associative. So if we can multiply it in any way we want. Okay, so A times B times C is equal to A times B times C, so we can define A times B times C as we would like. Also, when this is well defined, when AC is meaningful, this is a standard product of matrices, and BD is a standard product of matrices, then Kronecker product can be combined with the standard product of matrices. Okay, these are just some basic properties that we are observing. So this is just nice to have in mind, and we will see the many applications of these properties. Finally, when we transpose things and when we take conjugate transpose, then it behaves fantastically. Also, the last expression is tensor product. It coincides with dot product in a way that dot product of tensor product is product of dot products. Okay, so these are really nice properties. Okay, just to have in mind. Well, I'll come to that. Yeah, thank you. So these are the basic properties. You can just check it on the basic matrices and then just apply linearity in each coordinate. Okay. Now we come to a bit more interesting properties. We will use the well-known Schur decomposition, which says that although not every matrix can be diagonalized, each matrix can be written in upper triangular form in some orthonormal basis. So if you have r to the power of 3, then you can just rotate this r to the, sorry, this has to be a complex number, but imagine if it was real, you can just rotate complex c to the power of 3, and then you can write each matrix in the upper triangular form in this some rotated vector space. Have you seen this theorem? If not, this is very useful theorem for having a very nice form of each operator when you just do calculations with one operator. So when we apply this Schur decomposition theorem, then we can conclude that this Kronecker product behaves amazingly also with respect to eigenvalues and singular values. Okay, I haven't written singular values here. It will be on the next slide. So if we have two matrices, okay, I will leave this again here. If I have two matrices, A and B, and it has the set of eigenvalues something, and B has some other set of eigenvalues, just to have the same notation. So this is set of lambdas, and this is set of mu's. Then if we study the Kronecker product, its set of eigenvalues will be exactly the set of lambda j times mu k when we pass through all j and k's. So if there are n, for example, if there are n eigenvalues here and n eigenvalues here, we will have n squared eigenvalues here, and we will know that all of them are given in this form. Just for a simple observation, if you have two eigenvectors, let's say that ax is lambda x, just to see why we hope that it holds. If we have two eigenvalues for these operators, then using this property on the previous slide, when we take Kronecker product and when we apply it to a vector x o times y, then as we can see on this previous slide, it behaves very nicely. So this is a of x o times b of y, and this is lambda x times mu y. Okay, so now you can see that eigenvectors are preserved, and using Schur decomposition, you can check that when you write A and B in diagonal forms, so if you write A as Q U upper triangular matrix Q star, and if you write B as Q B, sorry, this is QA, QA, times upper B times QB star. Then by applying again the same result, you can see that A O times B can be written as QA O times QB times UA O times UB times UA, QA O times QB star. And now we'll get upper triangular matrix, and then you can read off all the eigenvalues. So this is basically the proof of this theorem. Okay, so when you have upper triangular form, this is why Schur decomposition is very useful. When you have upper triangular form in using orthonormal basis, then you can just read off all the eigenvalues. And this is basically the proof of this theorem. Now we have some more properties, because we will have many applications because of these many properties that hold. So how do operations like taking determinant and taking trace, do you all know what the trace is? This is the sum of diagonal elements. It's standard thing to study regarding matrices. Then you can check by yourself or using the Schur decomposition that determinant of the product is this weird change of exponents, but writing in a, if you see that determinant is a product, then when you take all these products, then if you multiply everything here, you will see that this exactly corresponds to the power of determinant in this way. Okay, this is just a simple consequence of the previous theorems, but we have listed everything here. And now we arrive to an important value of some matrix. Vieco mentioned this in his first talk. This is the singular value. So the singular value, the largest singular value is, as what he says, this is the amount that some operator, so sigma, maybe this is, I could have used better notation, but sigma max of A is actually, so what is the largest singular value? This is the most that the operator can push the vector which is on one ball away from the center. So this is like how much the operator expands the space. Okay, so this is the in L2 norm. So this is like how much A expands or contracts the space. This is the largest singular value. And all the other singular values, if you are not familiar, you will certainly be during your work here or anything doing mathematics. Singular value decomposition is one of the most important decompositions, which tells you like in what two bases to study the operator, so that you know that each operator can be written as one rotation, then expansion in all dimensions, and then another rotation. Have you seen that? If not, this is what you're going to study at some point, certainly. And we can see from the fact that singular value is eigenvalue of A star A, we can see that, so this singular value of A is a eigenvalue of A star A. And then we can see from the previous theorem that singular values of Kronecker product are multiplied this way. So if a matrix A expands the space at most 2 times, and the matrix B expands the space at most 4 times, then they're, sorry, not at most, exactly 2 times in some dimension, and exactly 4 times in some dimension, then their Kronecker product will expand the space in some direction for 8 times. So this is precisely equal to 8 times, not at most 8 times. So we have equality here. Like we know how much the tensor product of, sorry, Kronecker product of 2 matrices expands the space if we know how much each matrix expands the space. And we also have in the last line, using the previous property, the rank of product is product of ranks, and this follows from the fact that a rank of numbers is a number of non-zero singular values. So this is used in solving linear algebra problems when you don't have good conditioning. You just then study the singular value decomposition, then just discard the smallest singular values, and this is How you know that this is the rank of a matrix? Probably if you are studying computer science. So if matrix has rank 3, then it means that it has 3 non-zero singular values, right? You probably heard that if you're doing any linear algebra on computers, right? Okay, or you will hear that you're still young. Okay, finally, we have a slight generalization of this property. Instead of taking 2 norm, we can define a P norm to LP norm of a matrix. Has anyone seen this before? This is basically the same thing. If you just take what is LP norm of a vector? So if you take LP norm of a vector, this is just sum of pth powers. This is P to 1 over P. P needs to be greater or equal than 1, and this will be norm in a standard sense. You are sometimes you study these P norms when you want to consider problems of minimizing, solving some inequalities. If you want to, for example, if you want to solve some problems, this is a standard problem in, for say, when you work in Huawei, you want to see how to find the solution with the support of, like, if we have like 4 non-zero values, then you can minimize it in L2 norm, but since L1 norm is closer to this L0 norm that we want, then you will certainly have better results minimizing in L1 norm. This is like a standard trick used in compress sensing. If you haven't encountered that, then you again certainly will at some point. So these LP norms are different ways of measuring distances in space, right? And again, we define the LP to LP norm is the maximum expansion of a space when studying the operator on a one ball. We want to see how much it can extend the vector which is on this one ball. This is the LP to LP norm, but this ball can be in some other P norm. Okay, so this is like generalization of singular values, of the largest singular value. And this is called the operator norm in pairs LP to LP. We can also study LP to LQ and different pairs of spaces. Even we don't need to LP space, we can take any 2 norms and study to see how much the operator expands the space in these 2 relative norms. Okay, and again, Kronecker product has amazing property that we have exact equality here. If we can write an operator as a tensor product of 2 operators, and then we have like a correct generalization that if we know how much it extends, the operator A extends the space and operator B extends the space, then their Kronecker product extends the space as much as exactly as their product. Okay, so this is another nice property. Okay, and this is stated here. Oh, sorry, I copied it wrong. There is one property that I wanted to state here, and this is the property. Sorry, this is a typo. We know that LP to LP, when we have a standard product, it is less than A LP to LP times B in LP to LP. So when we study the standard product of matrices, this was supposed to be written here, I'm very sorry. When we study the standard matrix product, then we know if the operator A extends my space by 2 times and the operator B extends my space by 4 times, then the best I can say is that the product of these operators can be, it extends my space for at most 8 times. But when we have a Kronecker product, we have exact equality here. Okay, this is proved in these notes. These proofs are, this is exactly, this has one really nice trick, but I just want to skip the proof to go to see how all these really interesting properties can be used to solve some real world problems. Okay, so we've just studied a lot of properties. I told you many things, and I will now go to, in the second part, I will tell you how to use each of these properties to solve many problems. Just before that, I've defined until now just the Kronecker product of matrices. Okay, we have a matrix. We know we have this definition, which works really fine if we are working with matrices, but we are not always working with matrices in mathematics. We want to work with arbitrary vector spaces. Okay, and we want to define the similar thing for arbitrary vectors. Okay, we do not want to have always expansion of a vector in some basis. We want to define this object O times, which has the same properties as this object, but for arbitrary vector spaces. And how to do that? Where does this object live? So I want to define this O times multiplication. Maybe if you read some physical articles or books, then you just say, okay, I have this weird multiplication and it satisfies these properties. And all these other properties that are listed here. They just usually say, okay, this is, one can define this O times so that it satisfies these things. But what exactly is this O times? Where do these things, let's say, live? If you want to implement your library that uses this O times, how to implement it? What is the set of all these expressions, where it lives? Okay, this is an important question. So we can try to define it naively, and we can say for finite dimensional vector spaces, we can always, if we have a vector u, then it can be expanded in some basis as u1 times e1 plus un times en. And we can say, we can write this as a matrix form as u1, u2, un. Okay, so each vector in a finite dimensional vector space can be encoded with a matrix of dimension 1 times n. Also for any other vector space V, it can be encoded with some other matrix. And we can define this weird product as a matrix product of these two things. Okay? What's the problem with this definition? It looks nice, it's operative, it's actually very good. If you want to do just numerical computations, this is exactly how to do that. You pick a basis for your vector space, and then you define a Kronecker product of matrices in your library, and then just use it as a to define a Kronecker product of arbitrary two vector spaces. Okay, but when you're a mathematician, then you do not want to pick the basis at the beginning. Like, why is one basis more preferable than the other? If you want to change basis, how do these things behave? You know, you want to have some properties that are very general, and then that you don't want to pick basis in advance. And okay, so I told you you do it this way, but you can do it if you know some algebra. You can have like a better overview. This will be a bit abstract at first, but this turned out to be the correct way to define a tensor product. And so what do? We want to define this weird multiplication, okay, that satisfies all these properties. But we cannot do that a priori. We do not, as I said, we do not know the set in which these things live. So we define, formally at least, uv as a symbol. And then we can multiply these symbols, like take 1 times uv times u1 v1 times 2 plus 2 u1 v2, etc. And these two things are not equal a priori. These are just formal things. So this is something that you can do with formal expressions, and this is called a free vector space. So you take formal expressions of this form, finite linear combinations of your vector space, and now you don't even need to be finitely dimensional. You can define this free vector space over any two vector spaces. You take a finite linear combinations of the things of this form. You know how to add. If you have these two of the same vectors, you can add the coefficients in front of them. This is the only definition of the free vector space. And now, as you do with you've all encountered modulo operations, right? Modulo 6. What would you like with modulo 6? You would like to transform 6 and 0 into the same number, right? And now we would like to have all these properties listed before, so we impose all these conditions. Okay, we want this to be the same vector. So if we impose all these conditions that we want to be satisfied, then this is the set of conditions. So this is S, the set of conditions that we want to hold. Okay, and it is clearly subset of these formal things written here. I don't want to go into many details, but this is just so we have in mind, if you want to do it in an abstract way, how to do it. So we have some formal sum of expressions, and we have some other kinds of expressions that we want them to hold. And how do we construct modulo 6 operations? What do we do? How do we write modulo 6? We take all the integers and divide it with 6z, and this is like operation of identifying the two elements, as Ivan Novak had in his previous talk. So we now say take vector space of these assumptions that we want to hold, and this will be a vector space inside. This will be a vector subspace inside this free vector space. And since we can quotient vector spaces, we can define the vector tensor product of two spaces f as this quotient. So we have now imposed all the restrictions to be satisfied by this quotient. So whenever we have elements of this form, then they will be equal by definition. So exactly why 1 is equal to 5 modulo 6, sorry, not 7, mod 6, because 7 minus 1 is divisible by 6. The same way we do it here. Just because 7 minus 1 can be, this difference lives inside this vector space of restrictions, we say that these two elements are the same. So we define this weird product now inside this free vector space quotient by E times UV. So this is like correct definition, and now immediate consequence is the following that answers our, sorry, how much time do I have? Okay, 5 more minutes. It says that we have now constructed a vector space of these symbols in such way that each multilinear form is actually a linear form on this weird vector space. So this is the main theorem of constructing the vector spaces abstractly, so that now we have that each multilinear form is just the matrix multiplication on some weird vector space. And as an immediate corollary, we know that we can now impose conditions if and only if these vectors, defined in a weird way, are linearly independent in our newly formed space. Let's see how to do that in the first problem that we encountered. So we wanted to study if there is a bilinear form such that this should be E2, E2, right? Otherwise it's the same. So this should be E2, E2. So we impose some initial conditions, and then from the previous theorem that we just stated, we know that there exists a bilinear form that satisfies this, if and only if there exists a linear form on our tensor product of spaces that satisfies other conditions. So let's study the tensor product of these spaces. So tensor product of 1, 0 with 1, 0 is, when we recall the definition, okay, it's here. 1, 0, 1, 0, tensor product is, we take this 1, 0, place it at first place, and then this 1, 0 in the second place multiplied by 0, so this is 1, 0, 0, 0. Right? Also, the same with the second number, 1, 1, 1, 1, O times 1, 1 will form this. And finally, this last expression will be exactly this. Okay. And now we want to see if there is some linear operator that maps this first vector into C1, this vector into C2, this vector into C3, and this vector into C4. But this is now a linear algebra problem. Okay, we want to see if this multiplication is equal to C1, this multiplication is equal to C2, this is C3, and this is C4. But now we have all the tools from linear algebra, and we can do anything that we want to calculate the rank of this matrix. So the rank of this matrix is full. We can take determinant, whatever you want, what is the easiest for you. And you can see that as whichever numbers I put for C1, C2, C3, and C4, I can always find a bilinear form that satisfies this. On the other hand, for this second question, which looks very similar to the first one, just the last vector is now this. We can see that it's not always possible. Why? Because these three vectors are linearly independent, but if we multiply this by 2, multiply this by 2, and subtract this one, we will get the last one. Or where do you see it? Oh yeah, right. That's even better. So these two columns are the same. Thank you. So these two columns are the same. So the rank of this matrix is 3. So I have to be very careful how to define the bilinear form given the number Cj, and I can actually answer when exactly I can for which exactly numbers of Cj I can find the bilinear form in this way. Also for multilinear forms, you just write an O times something and you get the solution to all the problems of this type. Okay, and for the last example, really last example, these are very simple examples. Tomorrow we will go to more difficult ones. We want to create Hadamard matrices. This is like very standard problem in computer science. I won't go too much into that. We want to create a matrix which has only 1s and -1s, and whose columns and rows obviously are mutually orthogonal. And the question when such matrix exists is still an open question. So we know that necessary condition is that 4 must divide n, but we don't know if this is sufficient. There is some, I wrote it in materials, I think 668 is the smallest number for which we do not know if there is a Hadamard matrix of size 668. I think I should check in my notes. For which we do not know if there is a matrix with only 1s and -1s that is whose columns are mutually orthogonal. But as a simple consequence of our Kronecker product of matrices, we can see that one can construct easily Hadamard matrix of order 2 to the power of k. Okay, this will be actually, when you study, this will be character of groups f2 that Novak mentioned to f2 to the power of k. So you will almost certainly sometimes encounter this problem. So let's see how to solve it. And now, as we can see, this is a very simple problem. We just do it recursively. Sorry, I will just return back. We find a 2 times 2 matrix whose columns are orthogonal. This is obvious. If you multiply, if you take a dot product of these two columns, then it's 0. So we define the next matrix as this matrix O times the last one that we had. Okay, if you for homework you can multiply this matrix for H4 to see how it behaves, but inductively we can check that this is exactly this satisfies the problem just by using the properties written on the previous slide. So we just take the definition, insert the O times product where it's supposed to be, we apply the induction hypothesis and solve the problem. So in 4 lines we have constructed Hadamard matrices of size 2 to the power of k using only these simple properties. So in different fields of mathematics you can, by some coincidence, you can tensorize stuff to arrive to the solution of the problems. Okay, and I will stop here for today. Tomorrow we will continue with the next harder problems. Thank you. Are there questions? Thank you.
Thank you so much, Alexander. Are there any questions for Alexander? Yes, Mei-Ling?
I have a question about the permutation of matrix. Is there?
Permutation?
Yes.
Okay.
Is there a permutation can make? You can suppose the matrix. Each row of the matrix is a vector.
Okay.
And we can estimate their distance.
Okay.
Calculated.
Distance between
yes.
rows. Okay.
And there are someone they are closer one, someone they are far away from the others. Is there a permutation can make the closer one more close, the farther one more farther, more further? Yeah.
That's a nice question. So your question is if I take 2 matrices and I take a Kronecker product, if it will increase the what?
We have many vectors.
Okay.
And then we want to construct a matrix to do this permutation for the vectors to light the closer vectors more closer and.
But in what way? I don't actually understand it. So I have a matrix. Let's say A, and you said you want rows, A1, AN. So these are rows. And what transform do you want to do on this matrix?
Maybe we can group them like K group, and in the group, each vector they are very close.
Okay,
and
so let's say first K vectors are very close.
Yes, we can suppose it like that.
Okay.
Then we want a permutation, construct a matrix B, A multiply B.
Okay.
Then we make the like we can say the average distance in the group is closer, and for the distance for different group is further.
Sorry? K means,
yes,
yeah, but
yes.
with O times.
It's QR pivoting, that's all that.
Okay, but yeah, I'm not sure if it can be written this way. I haven't thought about it. I can think this tonight, but.
In Kronecker products, you have this perfect shuffle permutation, which allows you to have the Kronecker product commutative. So it's not commutative. But if you switch A and B, and then multiply it with perfect shuffle from left and right, then it is commutative. I mean, sort of up to transformation.
Yeah.
So I think many tricks with Kronecker products involve these particular permutation matrices, which allow you then to use standard linear algebra and conclude stuff that you want. I mean, in a certain sense, K-means is equivalent.
But what you take for the matrix B, I'm not sure.
Maybe one of the permutation matrices, or anyway, I'm not. I mean, it is something that needs to be thought through, but I think it's definitely.
It might be doable. Yeah, I'm not sure. Yeah, really, I haven't thought about this concrete problem, but you also have, this matrix will be bigger, so you will have to say what so. This will be a much larger matrix. So what do you want between these? So.
It's general product, not this.
Just a matrix product.
Yes.
But what then?
So it's yeah.
So I just want to choose a better base to make the yes.
I know what you want. I think I know what you want. But I would need to think a little bit. Go for the notes. So essentially, K means permutation is linked with QR algorithm with gold pivoting. There is sort of one-to-one link which I don't know having in front of my eyes, but I know of. So and in a certain sense, you're asking for a permutation. If you go to this high dimension, which will make this diagonal thick, like the matrix will have a thick main diagonal, and then the other blocks will be somehow thin. So anyway, I mean, I have seen these formulations. I know of the links, but I just do not have it in my sleeve. We can talk afterwards.
Sorry, but I think what you mean. So if you take these, so AK, let's AK is large, then you want AKAL is large, so you take some kind of Gram matrix. And this is, okay, this is what you say. Okay, I have a different. So you take a Gram matrix, and then your question is if we can embed this in some larger space so that it.
So essentially, you permute the rows so that the largest row comes first, and so on and so forth, so that they decay. I mean, that's.
But that's already this. I think what you might want is a Gram matrix, but I'm not sure. We can discuss this. I'm not. It's not clear to me what the concrete question is. Maybe.
The optimal would be you take the Gram matrix and then you sort its diagonal, and then you use that permutation to permute the rows or columns.
But what does it have to do with Kronecker product? This is what I don't see.
Okay, that is another question.
Yeah. Okay. Yeah. And so yeah, we can discuss it later. It's an interesting question, but I'm not an expert in this applied thing, so I have to think about it. I might know the answer, but not from top of my head. Okay. Yeah.
Thank you, Alexander. Any more questions from the audience? Okay. No? Okay, you will still have a chance tomorrow, because Alexander is going to have his second part tomorrow morning. And this first part concludes the day one of our workshop. And for this occasion, I would like to invite all of you for the dinner that will take place downstairs in a restaurant called Italian House. And it's going to take part at 6 o'clock. So we still got like 30 minutes, so you can refresh, rest a moment, and then we'll have some good food together. Thank you so much, and see you at the dinner, and then let's continue tomorrow at 10. Thank you.